Good morning, everybody.
Good morning.
Hey. I saw your video, Sandra, with your robot working. Great job.
We stayed up till like 2:30 this morning trying to.
What? You didn't have to go that far for it.
Well, I know, but it just wasn't. I had some things wrong on it, and I was like, I got to just start over. And so I'm glad I did because it works better. We found some instructions in my classroom, like that, I could have hands on.
Mm-hmm.
So it's a better robot for sure. It's a lot more stable.
Okay. And so how was your training yesterday?
Oh, it was long, but we covered 4 modules, so it went pretty good.
That's good. What math are you teaching?
7th grade.
Okay.
We
Seventh
kind of
grade.
went through what we'd be teaching every day, so we would have a and then eventually we've got to come back again, and we're gonna fix all of the tests, so they'll already be pre-made. So a lot of planning. Hopefully the year goes smoother.
Um. Yeah. So I guess that's kind of nice. I teach at like a small school, so we. So I'm like the only teacher that teaches the classes I teach.
Yeah.
So
Yeah, well, at mine, I'm the only 7th grade math teacher.
okay.
Yeah.
Yep. Yep. And also have a ton of preps.
Well, I probably will have 3 this year. Only had 2 in the past, so with robotics, I guess it will be 3 preps.
Mhm. So we actually did a good deal of programming yesterday. uh,
All
I'm
that
not.
will be on the video.
It should be. Has any of the videos been posted yet at all? On the.
Only to day 3, so yesterday's is not up yet.
Oh, okay. Okay. Yeah, the summer recordings.
Yeah.
Yeah. So yesterday is, but it'll probably be up sometime today. I'm imagining.
Okay.
Yeah. But we kind of actually we pretty much ended up working all the way to one all together. Like, well, but there were basically 4 programs we wrote for the 4 activity. Well, there were 5 activities, but one of them we kind of skipped because it was just basically copying the code that was already written there. So, but anyways, yeah. So we wrote code, and we each kind of took turns writing code for one of the activities. Like Miranda did an awesome job with her code. Oh,
I
what
feel
do you?
like I talk to myself while I'm doing the coding. I'm just talking out loud.
That's well, I mean, that's how I code too, so that everyone kind of follows along, right? Yep. I
Do
mean,
you know how whenever they were like whenever the kids were in like English in elementary school and you gave them like this or they gave you the sentence that had something wrong with it and you had to correct it. Do you kind of do the same thing for programming units for like Bellworks?
as far as like giving broken code to that would actually be some good practice for them for
Yeah,
sure.
it's just like a little 5 minute bell work just to, get them in. I'm just thinking out loud.
Yeah. That would actually be good, especially since a lot of the quizzes from here on out, I think the like starting with that unit 5 has a component where they have to like find the errors in the code. Yep. So yeah, that would be something to kind of get them used to that. But yeah, so we kind of introduced a lot of basic programming last time, and if you wanted to boil it down, mainly what we were doing was we were telling it to turn on the motors, so and then wait a certain amount of time and then turn off the motors, and that was pretty much what it amounted to each time. Now we ended up doing like we ended up like introducing some things like variables and things like that too. Um, but when you boil it down, that's all we were doing with the robots. We were just turning on the motors, waiting a certain amount of time, and then turning off the motors in order to go different distances. And all we did actually was just go forward and backwards with all those projects. So today we're going to introduce turning. And we're also going to introduce the motor encoders today, because the motors themselves are not just DC motors. They actually have some electronics and things in there that measures a lot of things. But one thing it has inside is what's called an encoder. And basically, what an encoder is like a little wheel that's on one of the shafts inside the motor, and that wheel actually has holes in it, and there's like a little tiny LED light on one side of that wheel and a little light detector on the other side. And so as that wheel spins, the light shines through the holes and it can count how many light pulses are going through it. So by doing that, it can actually kind of count like how much the motor has turned. So you can kind of so you can set the motor to just turn so many degrees. So instead of like having to do everything based off of time, you can get this more accurate way. So you can have it go the motor turn for just the right number of degrees you want it to turn, or the right number of rotations you want it to turn. Um, and so you get much more accurate like distances that you travel, for instance, that way. And so that's one of the things we're going to introduce today. The other thing we're going to introduce, so we're going to be covering units 6 and 7 today. And unit 6 is another one of these poster projects, but it's about the different kinds of sensors that we have with our robots. And so that's actually going to be our word for today too. So today's word is going to be sensor. So if you wanted to put that in Google Classroom. And yesterday's word, Sandra, was programming, was yesterday's word. But today's word is sensor.
You said program or programming?
Programming.
Okay.
Because we did a lot of programming yesterday. And today's word is sensor. So we're going to briefly talk about Unit 6, but it's just like Unit 4, and it's like one of these poster projects. So basically, there's a lot of different types of sensors that VEX uses, and basically you'll assign the kids, like each kid, like a sensor to do like a poster on, and kind of explain how it works. And if you actually have those sensors, you can have them even demonstrate the sensors, like putting them on their brain. A
Do they
lot
do this as their group or do they do this one individually?
this would be a group
Okay.
project. Yeah. Well, I mean, depending on how many of the sensors you have. Well, like for instance, there's a lot of sensors on the VEX store. You can obviously buy some different ones, but as far as like just the base kits don't really come with all that many. So there are, and actually there's some that we talk about that the kit doesn't have. Okay, so anyways, so let's start by talking about sensors. So I'm going to be sharing my screen again. Screen share time. But I do want to say I thought everyone did a really excellent job with their programming yesterday, especially since so many of you guys were new to it, or at the very least new to C++. So
I feel like it's a lot of like learning just nomenclature, like learning like the
yeah,
the
the different
yeah.
functions and commands. Yeah.
What was there ever a place we were supposed to turn our
I don't see one yet.
Okay.
And once
You
again,
know we did it.
yeah, I saw you do it. I was with you guys when you did it. Yeah, they only have activities up to 6.4 on here. I think, and I still don't have access. Well, I mean, I'm still listed as a student, not a teacher on here. So I might need to get Vanessa to remove me as a student, and then maybe I can use the teacher thing. Okay, but that won't stop us. We're just gonna keep on plowing forward. And it's Friday. So you guys have gone through. After today, it will be a full week of this class, and we've come pretty far if you think about it. Because we're looking at what, about 11 or 12 units in this class, so we're already about halfway done. And so I think that's an accomplishment in itself. At any rate, I think I'm sharing my screen right now. So let's look at these. This is lesson 6 or unit 6, and it's about sensors. But once again, this is kind of a short lesson where it's mainly going to be devoted to it's doing a poster project. And so what is a sensor? So let's anyone give some real life examples of some sensors that they see.
Don't you have like vision sensors?
Sure, but what are some sensors that you kind of interact with every day?
You mean like as in like your
Not-
your color or sight?
Oh well, yeah. I mean, I mean, as far as like electronics, possibly, but yeah, I guess,
Color?
Sensors on your car.
yeah. Yeah. So, what kind of sensors do you have on your car?
Backup.
Proximity sensors.
Yeah, distance.
Yeah. Yeah. So,
Yeah.
definitely, a lot of cars now have these proximity sensors, right, that let you know. And
Like
those.
lane assist. Is that what you're talking about?
Oh, what was that? I'm sorry.
Like lane assist, like if you get out of the
Yeah.
lane and then the steering wheel shakes.
Yeah, so a lot of cars have lane assist, and usually those are usually ultrasonic sensors, I believe, or yeah, usually they're ultrasonic. Um, so they use sonar to kind of let you know what's around you. But some of them are even like laser rangefinders in that case too. Um, and then you have, I mean, there's all kinds of sensors in your car, right? If you think about it, any sort of switch in your car is a sensor, right? Or you also have all the gauges on your cars, or those are getting readings from sensors, right? So you have
Yeah.
things like temperature sensors. You have to have some sort of sensor for your fuel gauge, right? So there's there's all kinds of sensors, like a simple light switch. A switch is a sensor. So you can kind of toggle it on and off.
What about your
So
microwave where you open the door and the light comes on?
yes, yes, that's a sensor too. Yep, yep. Knows when the door is closed. So
I guess a smoke detector too would have a sensor in it.
I always found it interesting how smoke detectors work since they're radioactive. Um, so they have that little bit of radioactive material in your smoke detector. I always thought that was kind of interesting. Um, so so sensors are any sort of physical device that can measure a physical quantity. And it says here they're indirect, incomplete, and noisy measures of the state of the world. Um, and so it is true that and you know this from chemistry, that any sort of measured value is not going to be 100% exact or accurate, right? There's always going to be um, some loss there when you take a measurement. And we can, the degree of precision we have, we kind of represent with sig figs with measurements, correct? So what are some types of sensors you can have. So here's some like a proximity sensor. Like a lot of you guys might have this. Um, Maybe you have a security system at your house where if someone walks into the yard, it turns on a light. So that would be like a proximity sensor. It's like a force strain or pressure. Um, that's very very common. Motion and orientation. So there's one type of sensor that's really useful in the competition robotics, and that is the inertial sensor. And it has like a 6-axis gyroscope and a 6-axis accelerometer all tied together, and so it can determine orientation, like which direction your robot's facing, and always kind of. And since it has that gyroscope, it always also knows which direction is down. So sensors that detect position and direction, visual sensors. So like there is in Vex that we have a vision sensor, and they have an updated version of it. And they don't even sell the old vision sensor, so we might want to think about updating those slides. But that vision sensor is pretty neat because it can kind of recognize objects of a certain color. And the newer AI version, they actually use AI to kind of train the recognition and they basically they kind of train it on the game objects each year, and so that it does a good job at recognizing the game objects for each game each year, even with like different lighting conditions and stuff. So that's kind of neat. So we can measure things like distance, we can measure light and magnetic fields, temperature and humidity, chemical and biological sensors, audio sensors. There are all sorts of sensors. So basically, any sort of physical phenomenon, you can have a sensor for it. And when we talk about sensors, we can kind of classify them in one of two categories. We can classify them as either like digital sensors, or we can classify them as analog. And so here are some different here's some different digital outputs and inputs here. So we got a digital clock here, or this is a multimeter, which if the kids are taking the engineering class, they'll work a little bit with these. And it can measure things like voltage and current and resistance, things like that. But as we can see here, it's got a digital display on it. And if you look at a joystick, then like this old PlayStation joystick. So this right here is what's called a D-pad or a digital pad. And the thing about digital, it's either always just either on or off, but there's really nothing in between. So like in these like digital panels here, then the little light turns on or off. And you can make these numbers by just a combination of turning on all these. In the same way it makes these numbers here. It's either these are being turned on or off. But it's all, and with a D-pad, you either press it or you don't. It doesn't detect like how hard you press it. So either you're pressing it and so it's providing that signal, or you're not pressing it and it's not providing that signal. So that's
So when I'm playing Smash Brothers, mashing the buttons harder does no good.
That's right. Now, I'm not sure with a PS5 controller or no. Some of your buttons actually are analog. Like, okay, so like for instance, I'm going to turn off my share. Just
Old
like
school
with
Nintendo directional pads were analog, and so that's why you could press them a certain level, and you would get walk, jog, run, whatever, depending on what you were doing.
Mm-hmm.
True.
So the buttons on this joystick here, all these buttons are digital buttons. So you either press them or you don't. But the analog sticks, the sticks themselves are analog because they do measure like how far you push them. So it's like if you just push it a little bit, like your character might or the robot will go slower, and if you push them a lot, then it'll go faster. So this has a range of inputs. So we would call that analog. The shorter buttons are digital on these, but most like PlayStation, Xbox controllers, the shorter buttons, at least the bottom ones, are analog. So like it does, like the more you pull on it, the like sometimes it'll be used like a throttle or something like that. So the more you pull on it, the faster you'll go.
I thought that the bumpers were analog on those remotes that you have too. The robot remotes too.
The on the robot remotes like these,
Yeah, I thought they were. They're not.
I don't
that,
believe that. No,
Okay.
I'm almost entirely positive they are digital, and we can. I'll share my screen. Like we can go into VEX code and we can add a controller.
The only reason I said is one year one of my kids turned those into the motor to the drive for the motors, and whenever they would do it, they were able to manipulate the speed. I thought they were doing it by pressure, but they might have just been tapping it. I just couldn't tell.
Yeah, I am pretty much 100% on that those are just digital buttons. Because when you program them like a digital button. Like you just like if we were to go in a sensor here and look at, yeah, like if I drag one of these in here, controller button, but you can change that to sorry, but like controller like button, yeah, because it just lists them as a button like all the other buttons. So basically it's just checking to see if they're being pressed or not. So unlike the other way, like you have like controller axis position, and that detects like a position of the controller axis, like for those. But yeah, so that's digital. And so if you look at like a digital signal, for instance, that signal is either going to be on or off. So like for instance, if that signal is on, it might send out 5 volts, and if it's off, it might send out 0 volts. So that's pretty much what's going on with a digital signal. So this would be just kind of like a standard square wave here. Now, that being said, you can use digital to approximate analog as well. In fact, that's pretty much what everything does with computers. Is that really, when you get down to a way a computer works, it's really all just ons and offs. It's just your bits, your ones and zeros. But if you have enough of those bits, then you can approximate analog, just like with just so many things. So, but here is some true analog things. Here we have a analog clock, which fewer and fewer kids these days know how to actually read one of these. Here is an analog multimeter. Basically, the more voltage you have, the stronger the electric field, and the more that needle's going to move. And then we have like our analog sticks. So once again, you can get a whole range of values out of analog. And so like here would be an analog signal. And notice here we're not just one or the other. It's not just 0 or 5. It can be like any value in between. In this case, or from 0 to 120 or to negative 120 in this case. So so you have a whole range of values you can work with an analog input or output. But as I said before, a lot of the sensors and stuff we work with will translate like an analog input into a digital output so that the computers can use it. Um, so inputs and outputs. So inputs would be, any sort of information that the sensors are collecting. And output would be what the robot's actually doing, whether it's printing something to the screen or if the robot's moving or anything like that at all. So when you're trying to select a sensor to use for your robot, there's a lot of criteria you want to think about. So you want to think about like the environment the robot's operating in. You want to think about the tasks that the robot's trying to perform, and what are going to be the best sensors for that environment and task. So, for instance, if I am building a robot to act like a Roomba, I have a couple of options there. So, like one, I could just add some bump sensors, some like bumper sensors onto my robot, so that it just when it runs into things, it will just kind of back up and turn around and move. And so, and bumper sensors are relatively cheap, uh, and they work really well. But the limitations of a bumper sensor is that it's actually got to come. The robot actually has to contact something. So if that robot's operating in an environment where like maybe there's a lot of delicate stuff that shouldn't be bumped into, then maybe I'll instead use like an ultrasonic sensor, like a rangefinder to detect how far away it is from an object, and if it gets too close, it'll back up without touching it. Or I'll use a laser rangefinder, which would do the same thing but with lasers. And then if I'm thinking about, okay, well, should I use a laser rangefinder or should I use an ultrasonic? Well, there's a lot of things I would consider there too. Like for instance, the price. Typically, the ultrasonic sensors are cheaper than the laser sensors. Another thing is the range. So if I'm trying to do things from much further away, the laser would be better. Or the type of objects I'm detecting. If the objects are clear and see-through, then and the laser passes right through, then I probably don't want to use a laser sensor, and I probably want to use an ultrasonic sensor instead. On the other hand, if the objects you're detecting are like really soft, like maybe you're trying to detect like a plush animal or something, then that might actually end up absorbing the sound wave and not reflect it back. And so in that case, a ultrasonic sensor would not be something you would want to use in that case. So a lot of things you could do. So a lot of things to consider with your sensors. So some issues with sensors are like noise. So like anything that's kind of giving you false readings, and depending on the situation, there's a lot of things in the environment that can affect how much noise you have. So for instance, an ultrasonic sensor, I mean, it could be literal noise that is affecting your readings, possibly. In other cases, like with a vision sensor, the lighting conditions can be a big factor providing, like they don't work very well on a low light setting. For
Yeah,
instance.
we had a lot of trouble with that on the FRC game. So when you would go to different venues and the lighting would change. So what they ended up doing is putting like ring lights around where the sensor was so that the lighting conditions were always the same. And it helped improve the accuracy of the robot really, really well.
Yeah, that's kind of why, like, one reason that they kind of phase out the old vision sensor, um, but and that's also kind of why, like, in the VRC field, you don't really see any teams really using vision sensors very often, because of since the lighting conditions will change so much from venue to venue. Um, and honestly, I really like what FRC does with their vision stuff. Like I like the fact that they use like the April tags on things. I think that's really cool.
Yeah, but
Um,
even the cameras trying to like see the April tags with the lighting conditions changing, it would mess up and it would make it a little bit off and they would miss. So they put those ring lights around it, and that really did fix the issue for the most part.
and so the ring light is just around the sensor itself, right? The
I believe
and
so. I believe so.
yeah. So yeah, and so does it still do okay even if like the object's kind of further away or
Yeah, it was mainly for like helping it auto align to the like when they had to like stick the coral pieces on the reef
okay.
to help it auto align for that. So yeah.
So but you know, so because by that point you're already kind of close to the object, right?
Yeah.
Yep. Yeah, that makes sense. Um and in fact, uh yeah, and in fact some of these sensors do actually have built-in lights on them like the color sensor. It has a built-in light. It is not called a color sensor; it's called optical sensors. But well, so anyways, so as far as the activity for this unit, basically whatever kind of sensors you have, you'll have the kids just pick out one of the sensors and then kind of do some research on it and do like a poster project on it. I know, for instance, with the EXP kits, at the very least, with the standard kit, it comes with a it comes with bumper sensors, like a button sensor. This is what a bumper sensor looks like, a bump sensor. Um, it also comes with a optical sensor, and an optical sensor. What it can actually do a couple of things. One, it can it can kind of detect when there's an object in front of it, and it can also, if the object's close enough, it can detect the color of the object. Um, it doesn't really detect like the position of the object in front of it like a vision sensor would. But basically, if there's a colored object in front of it, it can tell what color it is. And it also has this like motion function, like a gesture kind of function. So like if you sweep your hand one way in front of it, you can maybe have the robot do one thing. If you sweep your hand the other way, it can do something else. I found in practice that the gesture function of that isn't super reliable, but the color works pretty well. And in fact, that's what a lot of teams use is they use that optical sensor. So like when you're doing color sorting, like for instance, with this year's game, there's like red and blue cubes, and you want to kind of keep your team's color cube and maybe either get rid of the other team's color cube or maybe store it somewhere in your robot so the other team doesn't have access to it. And um, so you'll see a lot of teams using those uh, optical sensors to do their color sorting. Uh, and then another sensor that the EXP kits have, and I'm mainly saying all this for Lisa's benefit, is the laser rangefinder. So instead of having like so here's an ultrasonic rangefinder, um, which uses sound waves. The laser rangefinder instead just uses lasers, but it does basically the same thing. But there are some minor variations. Now, uh, the EXP kits don't come with these laser rangefinders. Oh, not laser, but they don't come with the ultrasonic sensor. But the laser rangefinder works well better in most cases than the ultrasonic one, anyways. Um, but that's pretty much all the sensor. Those are the only three sensors that the EXP kits automatically come with. But there are a lot of sensors out there. In fact, if you go to vex.com, so if you're inheriting a lot of like parts from like your previous teacher or whatever, let's go to V5. Um, And give me 1 second to pull this up. Let's go to products and we'll go to, this is so fast. I was just there. Why did I click? Products. Mhm. Let's look under electronics, and we want to, let's make set it to V5. We'll look at electronics. So here are some of the different sensors that we use in VEX. So we have that optical sensor I was just talking about earlier, and it can detect like colors. And it's not a ring light, but it does have a built-in light on it to more accurately measure colors. So we have our distance sensor, which has a little laser that shoots out the end. This is that inertial sensor that can measure orientations and rotations. This is a rotation sensor, and basically you run your axle. So like if you have a wheel or maybe an arm or whatever, you can run your axle through this, and it will measure how much is rotated. A lot of in the competition space, one way the students kind of measure where their robot is located on the field is they'll use tracking wheels on the robot, and so they'll use these rotation sensors to keep up with those tracking wheels. And then what else do we have? We have a potentiometer, which is kind of similar to a rotation wheel, but it doesn't really have the same range of motion of it. Um, a potentiometer is actually like what's like the knob on your oven or your washing machine or something like that. Those are typically potentiometers. And basically, what they have inside is basically a variable resistor. And so the more it's turned, the more resistance it has. And so by measuring the change of voltages there because of the extra resistance, you can get a range of values here. So basically, it's sort of similar to a rotation sensor in that you can run an axle through it, and then by turning it, you can kind of get a range of values there. But typically, like with a rotation sensor, you're mainly this is for like if something's like spinning, and so you're counting like how many rotations it's doing or how many degrees it's turning. Potentiometer, it's more like if you're just turning it from this much to this much, but you're not like doing like full rotations with it. And in fact, most potentiometers will only turn a certain range of motion. Like they may only turn like 280 degrees in total. And so that's the range you kind of work with.
Isn't that what
Now,
Matt Damon used in The Martian to talk whenever they did the part where he had to talk to him?
Such a
yes.
good movie.
Yep.
I can't wait for Hail Mary to come out.
Now, back in the old days of the Vex robotics, before we had the V5 brains and you had like your where you had like different programs loaded onto it. Back what we used to do with the old Cortex stuff, we would have a potentiometer, and basically we used it as a knob for selecting our different programs. So we just like mark we literally just stick a gear on there and mark a mark for where our knob is, and then we kind of drew on the robot like from here to here is going to run program 1, and here to here is going to run program 2, and so forth. And then like in their code, it would check the potentiometer, and if it was in this range, then it would run this routine. If it was in this range, it would run this other routine. So so that was the one way we used potentiometers way back in the day. Here's the new AI vision sensor. It's a little more compact than the old one, but like I said, they actually train the AI vision sensor on the new game each year. So like when you download the latest firmware update, it will have so that it can recognize the whatever the latest game objects are. And also the AI vision sensor also does recognize APO tags now, which is kind of cool. So I'm hoping in the future we'll start seeing some VRC games that use APO tags, because that would be really cool.
What are those?
So an APO tag is like a very simple QR code. And they look like QR codes. But one interesting thing about an APO tag is that by seeing that tag, it also knows the position and orientation of that tag. And so if it's like, say, stuck to an object, like maybe a game element or something like that, it will know the position and orientation of that object just based on the way that APO tag is facing. And so so basically, and FRC put out some some FRC teams put out some neat videos about April tags. But it's kind of neat because like from the software, like it actually can when you look at the overlay, like it kind of shows like the plane that that object is in. So it's really neat for object detection. And since and I think there's you can have like 255 different April tags. So you can assign like one tag for these objects and another tag for these objects. Or I think also FRC, don't they use them as for their their position on the field too? Don't they April
Yes.
tags on the field?
So like with this year's game, there was in the center of the field, there was basically what they called a reef system. And basically it was just a large PVC pipe or piping system, but it had basically like 8 faces because it was kind of like an octagon. And so there was an April tag on the bottom of each plane of that. So the robot would drive up, it would read the April tag so that it would know which coral pipe it was in front of. So that when you push the button, it knew exactly where to place the thing on the reef, and it would auto position so that it would line up perfectly to be able to bloop it on. Because some of them there were some of them that were even designed to actually like shoot the coral up, and it would fall if it was in the right position. It would shoot the coral up and it would fall directly on the pipe. It didn't even place it. So they had some really cool designs.
Yeah. And like she said, since it also kind of determines orientation as well, so you can tell if you're like lined up straight with it with that April tag, or if you're kind of crooked. So that's really cool. Now, Vex kind of has their own positioning system for VRC. You probably noticed with the newer field walls, like the portable fields, they have that. They basically have that barcode around the field, and that's actually what this other sensor reads. This GPS sensor. It's not a real GPS sensor. Like it's not a global positioning, but instead, what it does is it's basically a camera system like this AI vision sensor is, but it's been trained to read the barcodes on the field so that it can know exactly where it is. And there are some limitations with it. For instance, like if it's too close to a wall and it can't read enough of the strip, then it might not know where it is. But we purchased one of these to kind of play around with, and it actually works pretty well. It's a pretty good. Uh, uh, you may not want to rely on it completely, but it's a good complement to like your tracking wheels and things like that. So like it's a good way to like auto calibrate again, like if you need to kind of figure out where you are right now, which direction you're facing. And then well, it's through our expanders for. So you notice that a lot of the newer sensors, like these vision sensors, they plug in just like your motors do. But then we have sensors like this potentiometer here that just have these 3-wire ports. Your bumper sensor is the same way, and they plug into the lettered ports that are on the side of your robot. So that's how basically everything was plugged in, and with the old electronics, with the older stuff, they all everything just uses 3 wire ports, but a lot of that still carried over. So and then we have these bumper sensors, which are sensors, a limit switch, which pretty much works the same way as a bumper sensor, except for the thing about a limit switch, it's still just a button that's being pressed, but it has this little metal tab here. And the nice thing about that tab is it's flexible. So like oftentimes you'll use a limit switch for like say maybe if an arm is raising up and down, maybe you want that arm to lower until it gets to a certain spot and then stop. And you don't want to go any further than that. You can use like one of these limit switches. And since that little tab is flexible, even if it goes a little further, it's not going to break the sensor. It'll just kind of like bend that down a little bit.
So when the arm pushes down on the little metal tab, it detects like it's like, hey, you're touching me, so
Yeah.
stop moving.
Yeah, and if you look at it, it's just this little metal tab sticks out, and there's just a little button here. So like when the tab is pressed, and it just presses the button. It's really just a button. It's really all it is. So in a lot of ways, just like this bumper sensor. By the way, like the bumper sensors you have, actually are pretty stiff. So like for instance, when you're doing the Roomba project, that the robot has to kind of press pretty hard to kind of trigger it. So Vex did also release. So the ones you guys probably have all have like red caps on the bumper, and those are the more stiffer ones. But they also released these specific ones because a lot of people were complaining that they were too stiff. So these 6 Newton bumper switches have a much easier press, a much easier trigger to them. So if you're looking for an application and you need the button to just be barely pressed to trigger, then you may consider getting some of these. And these are the normal ones that most people have in their kits. But we also have things like line trackers, which is basically like it just kind of detects levels of light. And those are pretty cool. If you have any of these, I actually still have a bunch because I have a lot of old parts. One cool thing you can do with line trackers is, as it says, is you could like put a tape line down on the floor. And typically, what you would use is you would use these in usually groups of 3, where you have one in the middle, one on either side of it, and basically. Like let's say you have white tiles on the floor or a white floor, and you put like a black tape line down. So it can detect like light and dark. So if the middle sees dark, then it knows it can go straight. On the other hand, if like the right side sees dark, then it knows it needs to kind of turn to the left a little bit in order to line back up. Or if the right side sees dark, then it knows it needs to turn the other way. And so by using that, you can kind of like make the robot like follow a line around.
So that's like your lane assist kind of thing,
Um,
kind of where it's like shimmying to straighten up.
yeah, yeah. Um, People also use these as like optical sensors too, because since it kind of detects light and dark, if an object is kind of blocking it, then it's going to give a kind of a dark reading. So sometimes they'll use that in the place of an optical sensor. For one, they're a lot cheaper than an optical sensor. Because that's still kind of expensive for what it is. But that still works out to about $15 each. And then here's an actual light sensor that detects light and dark, but it's pretty much the same as a line tracker to that respect. And then these are the older shaft encoders. Most people will just use the new shaft encoders now. In fact, it looks like they're discontinued now. These are the older style button bumpers. The newer buttons actually have this cap and a screw. And what you can do is you can actually take that cap off in that screw. And since it has a screw hole, you can actually like, so for instance, like if you wanted like an actual full bumper, like across the whole front of your robot, you can actually like screw on like say a metal plate or something to the newer bumper sensors, whereas like the older bumper sensors didn't really have that option. But those are a lot of the main sensors that we use. Another one that you don't often think about is a motor itself. These motors that we have actually have these built-in encoders, and those are sensors. So here is actually like a cross section of one of these VEX motors. As you can see, the actual motor portion of the motor is actually pretty small. It's less than half the size of the whole motor. So this part right here is your actual DC motor, and the rest of it is some electronics and gearboxes. So basically, here's your DC motor, and then you have a gear here. So you got a gear here and a gear here, and then it transfers to this kind of long. This is like a gear and a long shaft, and then this is that gearbox that you can swap out. So like here, it's got the green insert, but you can swap out this gearbox for a blue or red insert. That the encoder is actually right here. So this is actually a round disc right here with holes in it. And here is the little LED light, and here's like that little optical sensor that picks it up. So it shines through the holes here. So that's a built-in sensor, and that's actually going to be what we're going to be looking at with lesson 7. So once again, lesson 6, pretty short. In fact, these slides right here, you don't really even need to share these slides with them unless you have kids that didn't like maybe do one of these sensors. And once again, you'll probably give them other things too. Like for instance, if you don't have a vision sensor, like if you have the EXP kits, you just assign them the optical sensor instead. Or and if you don't have the ultrasonic sensor, you assign them the laser rangefinder instead. And just whatever sensors you happen to have, you can assign them with. So any questions about this Unit 6 stuff about sensors before we move on? Like I said, the main concepts you're trying to get here are like the difference between digital and analog, and then just have them kind of research the different types of sensors that we would use and kind of present them to each other. Okay, so I don't really hear any questions for anybody. So let's move on to Unit 7 now. So in Unit 7, we're going to be basically going over 2 things. Like we're going to be going over how to turn, and then we're also going to be going over the encoders. And then, so we have a set of slides on turning. We have a set of slides on the encoders. And then we have a set of slides on turning with the encoders, using the encoders for turning. So let's look at turning first. So basically, first off, like an overview of some of the different ways you can set up your joystick. So there's a couple of ways you can actually turn with your joystick. And in fact, if you grab your brain and turn it on, and you pick drive on your brain, and then you click on, there's a controls you can pick. You can set different ways to control it from there. So you see, you'll have options that say left, dual, split, and right. So left means that you control everything from just the left joystick. So if you push up on the left joystick, it goes forward. If you push back on it, it goes backwards. If you push left on the left joystick, it'll turn left. And if you push right on left joystick, it'll turn right. And same thing if you pick right, it does all that with the right joystick. The method I like to use most is split. Split will do forward and back on the left joystick, and it'll do your turns on the right joystick. So pushing the right joystick right and left will do your turns, and pushing your left joystick forward and back will do your forward and back. And then, but then the other option you have is dual. And the way dual works is it kind of works how the robot actually turns, and that you use both joysticks, but you only push them forward and back. And oftentimes it's referred to like tank control because it's kind of like how tanks drive. And so basically, if you want to go forward and you got that set up, is you push both sticks forward. If you want to go backwards, you push both sticks backwards. And then if you want to turn, you'll pull one stick back, we'll push the other stick forward.
So
And
that's
so
like
like
the zero turn radius mowers where you're like,
yes, exactly like that. Yep. Yep. And so that's kind of what's going on. So that's another way you can drive. So some students like driving it like in the tank controls. And once again, that is kind of closer to what you're actually doing when you're doing your turns. Because when you think about it, when you're doing a turn with these robots, you're basically just telling like one side to go forward and back, and then the other side to go like in a different direction.
X needs to make a tank remote control where you have
Like levers.
like yes, that because if that was the case, then it would be extremely easy to drive in tank mode. But on a remote control the way they are, it's a lot harder to drive in tank mode. I mean, it's doable, but it's harder.
Yeah. I like I said, I and a lot of students like split arcade mode. One that's split mode. Um, one one nice thing about split mode is it's an easy lead into if you have a holonomic drive, because what you can kind of do is you can set like your left stick, your forward and back to going forward and back, but then you can set your x-axis on that stick for your strafe, and then you can set your other stick x-axis to the turn, and that way and since you have all your translational motion on the same stick, that will even allow for diagonals as well. So like if you're pushing forward and sideways, then it will kind of both go forward and strafe. Um, so that's usually the setup. Like you wouldn't want. So if you have a holonomic drive, like a drive that can move in any direction, you probably do not want to set it up so like one side strafe and the other stick is like forward and back and turning, because then if you're kind of pushing an angle, you'll be turning while going forward, and you probably don't want that. Yeah. So okay. So types of turns, we have point turns. Point turns is where one side's going forward, the other side's going back. And the center of rotation for a point turn is typically in the center of the robot, but it does actually kind of depend on the wheels you have and also whether those wheels are powered or not. So it's the center rotation is going to kind of actually end up being kind of in between where the powered wheels are. So particularly if you're using omni wheels. So for instance, like if you have a rear wheel drive where only the rear wheels are being powered, and if your front wheels are like the omni wheels that have the rollers, so there's no turning scrub, then what you typically find is the point of rotation is going to be like between the two rear wheels. So it'll be further back. And what that kind of means then is that when you're turning, your front end is actually swinging out more. Where like on the other hand, if you have like a front wheel drive, your center rotation is going to be, or your center rotation is going to be kind of between the front wheels, and that means when you turn, your back end swings out more. So and that can be like important. Like say if you have a claw in your front, um, if you have a rear wheel drive, then when you turn just a slight bit, since the front end is swinging out so much, then even just a small turn means like a big difference in how far the claw is moved. But if you have a four wheel drive, typically it's just going to be kind of in the center of your robot is where that point of rotation is going to be. Another type of turn you can have is a swing turn, and that's where you just run one side and you don't move the other side. Would be a swing turn. So instead of it turning like in place, it's going to kind of be swinging around. And oftentimes, what it'll do is when you do a swing turn, is it will kind of one of your wheels will end up being kind of like a pivot point. So like whichever wheel has like the most friction on it, um, on the opposite end of where it's turning, that will end up kind of being your pivot point that it's going to kind of turn around. That's kind of a swing turn. So that's another way you can do turns. Technically, you can have like a really wide swing turn by running, say, both sides forward. But if you run one side faster than the other, then it's going to do a swing turn. But the point of rotation is going to like be well outside the robot, and it will just do like a big circle around. So, like for instance, if you run one side half speed and the other side full speed, then obviously the full speed side is going to turn around faster. So that's kind of what's going on with our turning there. Now, so that type of turning, where you're running the two sides in different speeds, or running one forward and one backward, we call that like skid turning or skid steering. And when you're thinking about building a robot and thinking about skid steering, there's two things you want to consider: your turning torque. And your turning torque is basically the force that's being used to complete the turn. So it is the torque about the turning point which causes the robot to turn. And then you also have turning scrub, and turning scrub is the friction that resists the turn. And so those are the two factors that you're going to have. You're going to have your turning torque, which is helping do the turn, and then the turning scrub, which is resisting the turn. And typically, when you build a robot, if you want it to turn well, you're trying to kind of maximize the turning torque, and you're kind of trying to reduce the turning scrub. So, in our case with our robots, and let's say we have these normal wheels on it. So your turning torque is going to be the robot's turning, like the wheels actually turning on the ground. And that's in the direction of the force is, the direction the wheel's turning. So like if you're turning one side forward and one side backwards, then that's going to provide that torque in order to turn. Now, your scrub, on the other hand, that's going to become from your wheels sliding across the floor. And that's kind of one of the reason why we see with skid steering, like a lot of the wheels we use, we almost always use at least one set of wheels, being those Omni wheels, because those rollers allow the wheels to move sideways without much friction. But if you're just using standard wheels, then those wheels are going to kind of drag along as it's trying to turn. So that would be your turning scrub is that direction that it's the force being applied from the friction as the wheels are being dragged along the floor as it's trying to turn. Now, with a car, you don't really have that turning scrub because the wheels are actually turning in the direction that it's moving. Um, but we don't actually have that with these robots, so that's why it's turning scrub becomes an issue. Um, to really get the idea of the effects of turning scrub and turning torque, um, if you built a weird robot where your wheels were laid out like this, so that your wheels are kind of in a diamond shape pattern. So instead of your normal layout, if you have wheels like this, then you can really see the effects of turning torque and turning scrub. Um, because these side wheels that are powered by the motor, these are providing pure turning torque. There's no scrub at all because the because if we were how can I put this? Okay, so if we were to draw like a circle through all these points on the robot where the wheels are making contact with the floor, what we would see is the force from the turning torque is in tangent with that circle, and it's being generated completely in the direction that that it's turning. Is what I'm saying making sense there?
Sort of.
So, um, so imagine that like we have these 4 points right here, and we made a circle with them, okay? And um, and let's say we're trying to turn like this is our direction of turn, so we're trying to turn counterclockwise. In order to do that turn, then we need to have a force that's pushing in that counterclockwise direction, right? And that's what these wheels would be doing. They would be pushing with a force in that. So, like, if this is pushing up, that's counterclockwise on this side of the circle. And if these wheels are pushing down, then that's still the counterclockwise direction, right? So, with that circle there, so these are this setup. These wheels are providing all your turning torque because that force um, is is in all the force is in that same direction, tangent with that circle, and it's in the direction that we're trying to turn.
Makes sense.
Okay, so um, with that very same circle, though, if we look at these wheels and where they are tangent to that circle, you see that their scrub force because they're going to be sliding along the floor, right? And so as they're dragging along, they're going to have that frictional force that's opposing the direction of the turn. And so in this case, since that direction of that frictional force is also in tangent with that circle we drew, and so all of its force is actually in the opposite direction of the direction we're trying to turn here. And so all the force of these wheels that dragging along is going to be our turning scrub. Um, and since we're talking about torques, you know, like torque is force times distance, right?
Yes.
Okay. So in our case of our turning torque, it's going to be the distance from the center of the robot to these wheels here, right? And so that means that the wider this horizontal distance is, the more turning torque we'll have, right? Because even if this force is the same, if this distance is longer, then there's going to be more torque, right? And so what this kind of shows us is that the wider the robot is, the more turning torque we'll have. And in the same way, uh, so the longer the robot is, the greater the distance from here to this front here. So the longer a robot is, the more turning scrub we'll have. So if we're trying to maximize how quickly we turn, so if we want to build a robot that turns really quickly, then what we would want to do is have a wider, shorter robot. And that's going to be a robot that's going to turn really, really easily. If you take it to the extreme, you can look at those balance board things, right, with the two wheels on them. Those turn really easily, or like a Segway. Those turn really, really easily because they're wide but not very long. On the other hand, if you want a robot that resists turning and it has more turning scrub, so it doesn't turn, like maybe you have a robot that's traveling at really high speed, so you don't want it to turn very quick because it might like flip over or something like. Well, like, think of a drag racer, for instance. You notice how like a drag racer is extremely long, right? And they're also not super wide compared to how long they are. And that's because you don't want, when you're going really fast, you don't want to be able to turn like really wildly in any direction. So like when you're turning, you just want to make small minor adjustments to your turning.
Or a
Um,
skateboard.
Yeah, same thing with a skateboard. You don't want to have wild adjustment of turning when you're going at a high speed. Um, so that's why like skateboards are long but not really wide. Yep. So um, and that's also why those little two little things, they don't travel as fast as a skateboard could, right? Because since you turn so easily, it would be kind of a disaster if that were to happen. Um, so basically the gist of what I'm trying to say here is the longer the robot is, the more turning torque you're going to have. And the wider the robot is, the more turning scrub you'll have. So long, did I get that backwards? I did. The wider the robot, the more turning torque. The longer the robot, the more turning scrub. So if you want a robot that turns really quickly, you would want a shorter, wider robot. While on the other hand, if you want a robot that doesn't turn very easily, then you would want a longer, skinnier robot. So like for instance, in this robot here, this robot's going to turn much easier than this robot will. Now, however, another option, if you're worried about turning scrub, one way to eliminate that turning scrub is to use those omni wheels, because as you know, rolling friction is a whole lot less than a sliding friction. So simply by so even with a long robot like this, um, like if you had regular wheels and you did build a robot like this, you would notice that it would drag along the floor when it tried to turn, especially if it was really long like this, and it would have trouble turning. But if you swap these out to Omni wheels, then you find that even with these long wheels, because you pretty much almost completely eliminated the friction, the scrub torque, then even with this long robot, it's still going to turn relatively easily. Um, another thing to consider is your wheels. Um, so larger wheels mean a lot of things. One thing, if you have larger wheels, you're further off the ground. So that does kind of create less stability there since you're kind of higher off the ground and with smaller wheels. Um, Smaller wheels, it says here that smaller wheels will increase your turning scrub since they're farther apart from the turning point. I guess that's true. If you were to consider like the wheels being, if like the outer part of the wheels was in the same position, then where the wheel is contacting the floor is a little further away than where the wheel is contacting the floor on a larger wheelbase. So that would be a little more friction. Um, in practice with our Vex robots, since we're always using Omni wheels, we don't really concern ourselves too much with that though. Because once again, changing our wheels has a huge impact. So so here we have a robot set up with a front wheel drive, and we have these Omni wheels in the back. So that pretty much eliminates the turning scrub here. So what you would kind of see here is the point of rotation for a point turn is going to be kind of in between these wheels here. So like they have it kind of marked with a piece of tape, and you could try doing this with your kids too. Uh, you could have them maybe write a program to slowly turn, like with a point turn. And you could just write that as like maybe setting the velocities to 25% and just having the front go forward and or the left go forward and the right go backwards. Um, and what you would kind of see there, and I would kind of do it kind of slow. If you put that tape at the point of rotation correctly, when they look straight down the robot, they should see that as the robot's turning, then that tape really shouldn't be moving any. It should be kind of staying in the same place if they got their point of rotation right. Similarly, if you were doing like a swing turn where we were just running these wheels but didn't run these wheels, you would kind of see that point of rotation would be kind of around that front, like probably underneath that front wheel is what the robot would kind of turn around. So here's like a little short video showing that swing turn. Um, I don't think they had it perfectly right there. um, but you did see that it was turning pretty much around that front wheel, right? And then
You could also put it on put the robot on like one of those big notepad papers and have a pin touching the paper and thread it up through this where they think the center, like where they think the point of rotation is going to be. And hopefully that it would mark it, or that mark would stay and it would rotate around so that they could like see if there's any variance with that. Might be kind of cool.
yeah, or I mean, even yeah. So that would be so you can see if the pin stays in place to mark. Also, if you just put the pin anywhere else, the circle it transcribes should be around the center rotation. Like the center rotation would be in the middle of that circle that it would.
That'd be kind of cool to see that.
Yep. Yeah. And then here's a point turn. Once again, they probably don't have that perfectly there, but it's pretty close. And once again, um, yeah, if they were to put a pin at that point at the center rotation, then it shouldn't really move at all. But also if they, like you said, you could put the pin anywhere on the robot, and the circle it transcribes, the center rotation should be in the center of that circle.
Once you probably get a little bit of drift, no matter, I mean, it'll be almost impossible, I would think, to make it perfect.
Oh
Yeah.
yeah. But just so they could like
Friction and
see
stuff like that.
yeah.
Yeah, and once again, that's the difference between our ideal situations and real life. Yep. Um, and then once again, they should always kind of consider the center of gravity. The center of gravity actually matters with your turning too. So if you have more weight on, say, the back, then that can affect your friction on those wheels, which also can affect your your trans. So for instance, like even if all even if it was all these wheels were powered, um, let's say we had it set up like when we built our gearbot. So we have motors in the middle, and we're running all four wheels, and every wheel was an omni wheel. Um, Even if you have that setup, it might not be exactly in the middle, simply because if you have more weight on one side of your robot than on the other, then that weight is going to press those wheels in more and create more friction, and so that will also affect your center rotation. So so it is hard to really nail it down, but you can kind of get an approximate idea where your center rotation is going to be. Um, so how will we do a turn in our Vex code? So basically, we can do our turns. Well, at least what we learned so far before we introduce these motor encoders. We can do our turns just like when we're going forward or backwards. Basically, we're just going to turn on some motors, wait a bit, and stop the motors. But the only difference is that we're just turning on the motors in different directions now. So if we kind of read through this code here, and it looks like it's been commented pretty well, we can say we're setting the motor speed. So we're setting the velocities of these motors. And then we're turning on the left motor, but we're spinning in reverse. And we're turning on the right motor and spinning it forward. And then we're waiting a certain amount of time. So we're waiting 1.25 seconds. And then we're stopping the motors. So this is going to, in this case, this is going to do a left turn, right? Because if the left motor is going backwards and right motor is going forward, then it's going to do a left turn. Or we could say that's a clockwise turn. No, sorry, counterclockwise. The left turn would be counterclockwise.
How did they get the estimated time?
Well, that's a good question because I can tell you for sure that that is wrong. Well, it depends on the gear setup they have. Um, we will. Okay, so in the actually in the next, not even. Okay, in this lesson here, in the 3 lesson, we will kind of learn how to calculate how we can figure that out. But it does it with the encoders, not for time. But you can do it with time too. I guess, yeah. It won't. It is a really good question to ask. And the way you can calculate that is so if you know how do I put this? Okay, yeah. So if you know your point of rotation, and you know kind of the circle it's transcribing, right, or where the wheels are making contact with the floor. So for instance, let's let let's say we have this setup right here, okay, and let's say our turning point's in the middle, and basically where these wheels are making contact, what you can do is you can measure from your point of rotation to the where the wheels touching the floor, and that would be the radius of that circle that that point turn is doing. Does that make sense so far?
Yes.
Okay. So if you have the radius of that circle, you can also get the circumference of that circle, right?
Correct.
Okay. And so if we wanted to say turn 360 degrees, we would the distance that the robot would need to travel would be the distance for the full rotation of that circle, right? So the full circumference of that circle.
So 90 degrees would be a quarter of that circle.
Yeah. And so So basically what you're trying to do is just like with a linear distance, like you calculate how far it would go, would need to go for, so many inches. So, but if you figure out a quarter of that circumference, then that would be how far the robot would need to go to go a 90-degree turn.
Okay, that makes sense.
Yep. And that's basically what we'll be doing with the lesson 7.3 is we'll be doing that to calculate how far we actually need the robot to travel to do a turn that flip.
Wouldn't
So
you
that
also need to take into account your wheel size to figure out how many rotations of the wheels
yeah,
would make that distance of the circumference of the quarter circumference?
you would.
And then if you know the RPMs, you can just find your time and then just use your speed times your speed. And then you'd have your speed times your distance to figure out your time.
Yeah.
Yeah.
So basically you're using the circumference of the turn that it's doing, of the circle of its turning, to get your target distance that you're trying to that you're trying to get the robot to travel. And then you're just doing all that dimensional analysis before to go to a certain distance, right? And doing that dimensional analysis stuff is where you're factoring in things like the gear ratio and the wheel circumference and things like that. So but basically once you got your distance that it needs to go, it would be just the same as doing the dimensional analysis for a linear distance. You would do the exact same thing as we did in unit 2. So back
Okay,
to
sorry.
this
Before you
code.
move on, so if you have a rear wheel drive, then your center of rotation would be in between the back wheels. Is that right?
Yes.
Okay.
Yes. And so in which case you would actually want to measure from where it's, because especially, okay, so in that case, the circle that you're kind of making would be the circle between the wheels that are actually the powered wheels. Because if you kind of think about it, especially if you have, like, okay, so this setup, these rear wheels aren't really doing anything to affect how it's turning. Because we got these rollers on it, so there's really not even turn scrub to worry about. So you're kind of concerned more about the circle that these wheels are making. So in that case, the radius you would use for the circle that it's moving would be from the center rotation to these wheels. So to whatever wheels that are actually power and driving the turn.
Got it.
This might be a little beyond what the kids would have asked, but if you keep that same picture and we're doing what you just talked about, where the center point should be where that yellow tape is, but since there's so much more mass towards the other side, even with the reduced turning scrub, shouldn't there be a movement of that?
Yeah. But it's really uh it it's really hard to nail that down without like just experimentally finding the actual center rotation there. But your approximate center rotation is still going to be between there. Even well, there is an extent because obviously one thing, if you had too much weight on the back, these wheels right here might not even get any traction to turn, right? Because if you got, like, for instance, if you have so much weight on the back that it's almost tipping from the back, and these wheels are just barely touching the floor over here, then even if these wheels are spinning, they're not going to get any traction, right? Um, and so you might barely turn at all in that case. Did Josh like just pop in and out again after?
Yes.
Yes, I'm getting frustrated.
I think you're doing it on purpose. You ask a tough question and you pop out so you can hear the answer.
No, I really wanted to hear the answer. I was sitting there, and then all of a sudden, I'm like, I'm talking. I kept talking, and then I was like, I'm talking to myself, aren't I? And nobody answered. So I was like, yep,
It's
there it is.
okay. It's Friday. It's okay.
No, but this is what we deal with every day at this school, and it drives me up the wall.
That's why I didn't even bother going to school to do mine.
Well, but what's sad is where I live, the school's internet's still better than my internet.
Yeah.
Need to get
Actually,
some Starlink. Starlink's awesome because I live in the woods, but I have good internet.
Yeah. So, how much? What was the last thing you said, and what was the last thing you heard earlier, Josh?
Well, I was in the process of asking, shouldn't the tape be moved more towards the brain if there's more mass where the claw is? Um, shouldn't the center of rotation be moved more, basically where that frame would X right in front of the brain, where the claw and the frame X? So
Mhm.
basically a little up and to the left of where the tape is. Wouldn't it move a little bit more that direction if there's more friction created by the heavier mass up top? And I know that we have low scrub, if any scrub at all, with the Omni wheels, but just wouldn't it move a little bit?
Yeah, and but once again, it's really going to be kind of hard to pinpoint that without experimentally finding it.
Right.
Um, and the best way to probably experimentally do that is once again like you could do something like put a pin somewhere and let it draw a circle and see where the center of that circle is. But um, and to the extreme, like you could end up having so much weight on the back um, that like to the point where it's almost tipping over. In which case, that these wheels are hardly making contact with the floor at all, and 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 there would hardly be any turning torque at all in that case, right? Like the wheels would just kind of spin out. Um,
Yeah.
so so but for a general approximation, it's going to be approximately between these two. But you are right that the more mass we're going to have on the back, the more even with Omni wheels, the more turning scrub you'll have, and then that will kind of affect where the center rotation is. That's and that is true. Yep. Um, so, um, and that also kind of means like when they're doing their stuff, it's not going to be perfect by any means.
But they could get in the ballpark and then just
That's
make
right.
adjustments from there.
Exactly. And that's yeah, so and that's kind of what I tell my kids too, that the calculations will at least should get you in the right ballpark, and then you can kind of make your fine adjustments from there.
Yeah,
Um,
this was more, I mean, the point of the question for me at least was more for, I might be teaching this class to freshmen or sophomores or something like that, but then I might have kids on my robotics team that are a little bit more junior, seniors, higher level. And
mhm.
so whenever they're not understanding something, it's like, okay, well, let's go back to this concept that we learned a couple of years ago. Yes, it should be there, but this is happening and causing it not to quite be there. And I'm just trying to, like, basically all the kids that I'm going to get are going to go through all my engineering courses and physics with me, and so it'll be kind of a progression. I want to make sure that I, I have that ready for them later on.
Yeah. Um, and yeah, and I think this is actually a really good foundation for them, so that they'll kind of see this. So when you get to physics, things will start kind of clicking more, right? At least that's the
Definitely.
hope.
Yeah, I mean the kids who I've had who have gone through some of the engineering courses, obviously not this one, but the other engineering courses, the ones who didn't take physics, they they get it more. They might not necessarily, we do AP physics. They might not necessarily score out of the park, but they get the concepts better,
Well,
which is all I
even
really care about.
if it's physics, it's not supposed to work anyway, right? Isn't that the idea? If it's chemistry, it stinks. If it doesn't work, it's physics.
That's right.
Yep. So before we move on to lesson 7.2, which is about the encoders, let's look at, there is a at least one coding thing, activity. Actually, there's a couple of them, or is this all the same one? Let me look at, see what these are. It says activity 2. What's activity 1? This is probably activity 1. Yeah. So let's look at these activities here before we move on to 7.2 part. So in this particular, we're doing a turn investigation for time. So it says, in this investigation, we'll complete calculations for swing turns and point turns. And once again, a swing turn is where just one set of wheels moves and the other doesn't. And a point turn is that one side goes forward, the other side goes backwards. So let's look at the procedure for this. So we're going to write a code in VEX code that allows your robot to execute a 90-degree swing turn by manipulating your time variable until you have achieved a 90-degree turn while keeping the power at 50%. In your engineering notebook, record the time in the first data table below. So we're going to repeat this step, but change the power to 100%. And engineering notebook, record the time below. And once you've adjusted the code for an ideal 90-degree turn, predict how long it will take for your robot to do a 45-degree turn and an 85-degree turn, 180-degree turn. And that's like the part 2 here. It may be difficult to be precise in the error as you are measuring on the floor. I'll repeat this. This can be accomplished by putting like a 45-degree tape line on the floor. Repeat this process. So basically, what you're going to have the kids do is write a very simple code. And actually, since Sandra's with us today, I'm going to I'll go through writing this code, and I'm going to kind of explain it as I'm writing it, because it's going to be very similar to the stuff we're doing yesterday, and probably need to, show Sandra what we're doing to write this code. But basically, what we're going to do is we're going to write a code to try to make a 90-degree turn. We could actually try to do the math on that and see if we can kind of figure out what time. So maybe we'll do that too. So let's try to figure out the math first. Like, how many seconds do we need to pull off a 90-degree turn? Now, on my robot,
at the 50% power level.
At the 50% power level. So that'd be 50% power is 100 RPM. And since my robot's currently set up for a 1-to-1 gear ratio, let's consider that. I was going to grab a tape measure if I have one in here. I do. I think the last time I measured this, since I have a 4-wheel drive, I'll be just kind of measuring from the center of the robot to a wheel. And that's roughly about 5 inches is my radius. So if my radius is 5 inches, then my diameter is 10 inches. And so my circumference is going to be 10 pi inches. So that is the target distance that I'm shooting for. So I'm shooting for going a distance of 10 pi inches. Well, that would be for a full 360-degree turn.
Yeah, you got to take a quarter of that.
Yeah. So so in that case, we're trying to go 2.5 pi inches, right? Now, I would suggest leaving that in terms of pi, because
Okay.
what you'll see is that the pi's will cancel out when you
True.
factor in your when you do the step with your wheel diameter or wheel circumference. So why don't you guys try seeing if you can do that calculation. So so the distance we're traveling is 2.5 pi inches. And I want to know how many seconds it's going to take to go that far. So let's see if you guys can do that dimensional analysis again for that calculation. You might want to refer if you took some notes from, or if you did the calculations and you still have them to look at.
We're assuming 4-inch wheels. Yes.
Yeah, yeah, because that's the wheels you have on your robot probably. So
If I did this right, I got 0.375 seconds.
that is also what I got. So not very much. A third of a second. So that's barely going to turn at all. Honestly,
You said 0.375, right?
yeah.
Or 0.374 is what I got, but I rounded, so
Well, yeah. Well, once again, those pies will cancel out, so you should end up with a pretty clean number.
well, I rounded I rounded in a couple other spots earlier on. My time and stuff like that. Whenever I was converting.
Oh, okay. Yep. Because I ended up with just a really clean 0.375. There were no like other digits in that.
Yeah, it was an exact number for me too.
Yep. What about Lisa and Sandra? Were you able to kind of do that calculation, or do you want to see what that looks like?
No,
I-
I left
Yeah.
something out, so I did not get 0.375. I left something out.
Okay, I'm gonna hold up my paper. It's the one on the bottom here, if you can see that. But you see, well, we started with 2.5 pi inches, and we turned it inches into rotations by using the circumference of the wheels. And then we turned the rotations into minutes because it's 100 rotations per minute because it's 100 RPM. And then we turn the minutes into seconds.
I definitely need more practice on this.
Yep. Okay.
So just a little maybe helpful hint, Sandra. If you have like conversion factors, you know that you're going to be using a lot. I always like to like just put those like in a box above my problem so that when I'm like, okay, I'm starting with distance, the only thing that's related to distance is the wheel with the distance to rotation. So like you can say, okay, there's a pi inches that I'm starting with. Let me find the only conversion factor that has pi inches in it. And then you'll say, okay, that's the one I need to pick.
Okay.
So that might be helpful. I'm not sure.
Yeah, I got my I got my rounding from. I calculated the speed first. I went to my physics brain went to the speed equation in my head immediately. So I was trying to get distance, time, and all that stuff. And so whenever I rounded it to 1.67, that's probably where I got my point, whatever it was, off of what y'all had.
Yeah. And anyway, and this is just an approximation, anyways. Um, okay. So, but we noticed that number is a that's a very short. That's less than a sec,
Yeah.
like about a third of a second. Um, so one thing I would recommend for this assignment is have the kids put on the high torque gear setting if they still got their gears.
So
Um,
they can turn slow, like it'll.
yeah, so it'll turn a little slower. It will help a little bit, not much. So in fact, that's what I'm probably going to do. I'm going to swap out the gears on this. So what would that be? We could just take this and we can multiply it by 7/3 is what we could do. Um, so our point 375 times 7 divided by 3, and that gives us 0.875, which is still under a second.
Out of curiosity, why wouldn't they have done a full circle there? I would have thought doing a full circle for your initial test would be better because it would, how do I put this? There would be less error in it than doing um, a quarter turn, or are they shooting for like, am I missing what the point of the initial test is?
Well, one reason is a quarter turn, a 90-degree turn is useful. So if they have, in fact, in lesson the next one, well, let me go to the next. Yeah, this is it. So the next activity is they're basically going to make a robot to drive around this object here. And typically they'll want to do like go forward, do a 90-degree turn, go forward again, do a 90-degree turn. And the way I did, they say 4 foot here. I what I do, since I have squares and they're 1 foot squares, square tiles, I basically put a tape around one of the squares, and then I have like a 2 foot radius, and then so it's like five. It's like a 5 by 5 square. And what they have to do is they have to make one full rotation, or one full revolution around that square and come back to where they started without crossing any of the lines. So they can't like bump into the inner and they can't bump into the outer. And
I
so,
think Daniel does something similar to that.
yeah. And um, so if in the previous lesson they've already kind of nailed down what their 90-degree turn is, then they can use that data for this next assignment.
Yeah, well, no, what I was meaning was just from a purely the investigation portion of it.
Yeah.
If you do the full circle, I'm thinking of all the little things that happen whenever you try to turn a robot, like something jumps or whatever the case may be. And so if you're only doing a quarter of a turn, you might have issues with it jumping, and then obviously timing issues because it's happening so fast.
Hmm.
So I was just thinking from an investigation standpoint, if you did a full circle, the jump doesn't affect the total time as much as the jump would affect the time in a half or quarter circle. And so now you allow it to go all the way around, and you have less error, human error on the part of the person who's timing. I would just think you would reduce some of your error by doing the full circle and dividing it by 4 than you would trying to do a quarter turn and get everything as accurate as possible.
Well, okay. First off, they are not. They're not timing it, um, because you're writing a program and the robot's just running that amount of time. So you don't really have the human error in that respect. But you do have, like you said, you do have the robot error with the jumping and everything like that. Um, but they do actually need, with all that into account, they do actually kind of need to have that 90-degree turn anyways. Um, uh, Even with whatever issues it has, they still need to kind of nail that down. Is Am I making sense of what I'm trying to say?
So basically, like if they've got a robot that they've built and they're going to be using that robot for a bit for like
Mhm.
these different activities. So if they can like they get themselves in the ballpark for the 90-degree, and then they can just make auto adjustments within their code by going back and changing that number, that like timing number, and then they
Mhm.
can like be like star like use this number like with this robot, usually use this number for this turn, and they've got that as a reference point, maybe.
Yeah, exactly. Um, because
I misunderstood the first part of the code. I thought that the original part of the code was we were just making the robot turn at 50%, and then we were timing a 90 degrees worth of turn.
no,
So we're
we
actually trying to time it out. Okay, I got it. Never mind.
yeah, so we're trying to yeah, we're adjusting our timing number until we get a perfectly 90-degree turn.
Gotcha.
Is what we're doing. And so what we did is we just calculated like a ballpark for that 90-degree turn. And then we're going to just adjust that number until we actually hit 90 degrees. Um, is what we're doing here.
Okay, that makes more sense.
Yep. Um, and honestly, I have a few issues with this simply because the, especially at the 100% power level, it's really hard to, for instance, if they're using 1:1 gear ratio and 100% power level, uh, it can still pull off, but we're talking about like a tenth of a second, so the robot is like hardly like twitching. Um, and so I would, and you might want to consider this as maybe instead of doing power levels of 50 and 100, maybe power levels of like 25 and 50. Because once again, that would give them longer times and a little better to work with. But
Are we
yeah,
allowed to like as the instructor in our course,
yes,
are we allowed to make those adjustments to LSU stuff for our kids? As long
yes,
as we like make a copy that is our copy and not theirs.
yeah. I mean, yes, that's exactly right. So
Okay.
you don't have editing access to this, but you can make a copy of it, and then yes, so you are definitely within your rights to make adjustments as you feel is necessary. Yep. And this
Because
is
I mean,
one
you're
of
still
those.
learning the same thing. I mean, you're
Yeah,
still doing everything the same. It's just you're making it easier for you and your kids to get the data properly.
I agree.
yeah. So no, you don't have to rigidly follow everything like it is, because even now even after like doing this for 5 years, I still find some errors in here every now and then. Anyways, um, but yeah, and even like for instance, the final project is just a suggested final project, and there's a lot of ways you can do a final project for this. Like, so you can do like something completely different for your final project. Um, and the ones they have suggested are just suggestions. But yes, any of this stuff you can modify it how you need it. Yep. And this would be one of those changes I would probably recommend would be to set it to 25 or 50. However, That being said, even with these values, 50 and 100, it is still doable because I've had my kids do it, and they are able to pull it off. So you can leave it like this. In fact, this has been changed since the way it originally was. It used to be, and they figured out their time, and that they were using that time and figuring out the actual angle, and they were using the angles as the for the error. So, like for instance, like you were trying to hit 90 degrees, but actually went 92 degrees or something like that. But in practice, it's really hard to measure a precise angle.
You're
Like
assuming they know how to use a protractor.
yeah, and even if you have a protractor, you know you got to put that protractor at the center rotation of the robot to get that angle, right?
Yes.
Um, and then also you don't have like a giant protractor.
You
So
have to
this is
put a string on to make like a sundial thing, put a string on the end, drag it out. It would be a hot mess.
Couldn't you just
yeah,
take a big piece of paper
yes,
and use
and
the corners of the
and
paper?
that was actually the way we used to do it. We took like a big sheets of paper, and we would mark it that way. But even then, it was still a mess. It was so I was actually the one that suggested we just do it off the time because you can pretty easily um, know when the robot has turned 90 degrees because especially if you have a tile floor like mine, but even if you don't have a tile floor, you can just put a tape line. And as long as you have like as long as you have the back of it lined up to the tape line, and then when it turns, the side of it now should be parallel to that tape line when it's at 90 degrees. Um, and the same thing with the 180 degrees. If the backside's lined up the tape line, then when it turns 180 degrees, the front end should be parallel with the tape line. So
Or you could go old school and put a little cheap compass on one corner and get it facing due north, and then whenever you rotate, now it should be facing either east or west, depending on which direction you went.
yeah, yeah. If you've got some magnets, I mean some compasses to break out, just be careful where you put them though, because for instance, the brain has little magnets in them for a faceplate to hold the faceplate down, and the motors obviously have magnets in them too. So those might throw off the compass readings. Um,
Yeah, I was thinking put it in a corner as far away from everything as possible, or maybe if you have a claw, put it on top of the claw, like just tape it up there or something like that.
yeah,
Maybe not on the claw itself, but on your tower for your claw.
yeah. Um, so yeah, so you could maybe use a compass to accomplish that too. Whatever way you think's easier. Like since once again, because I have those floor tiles, what I do is I just use the floor tiles, and then I'll I'll lay down some tape for a diagonal line to have my 45 degrees, so the robot for the 45-degree turn that it's lined up parallel with that diagonal line. Um, but you can accomplish the same thing with just some tape on the floor. You can just you know you can lay out 90-degree and a diagonal, and just making sure it lines up parallel with those tape lines to pull that off. So but at any rate, so we had calculated what we're going for, so we know approximately if I swap out the gears on this in 0.875 seconds it should do about a 90-degree turn. But then we're going to kind of adjust that until we kind of hit it. So let's write a program to do that. So I'm going to go to Vex code, and that's code v5.vex.com. And I'm going to discard this. And it's approaching 10 o'clock. And this is usually the time when we take a break. Do we want to take a 10-minute break before we write this code out?
I think that's a good idea.
Okay. So let's take a 10-minute break. We'll come back at 10:10, and we'll write some code for this project. So we're going to take a 10-minute break. Ooh. Okay, are we all back? Is Lisa back? Yep, I guess so. Okay, so we were about to write a program to do a 90-degree turn. So what I'll do now is I'll go ahead and share my screen. And for most of you, this should be familiar from yesterday. So what we'll be doing is we'll be going to codev5.vex.com. And we're going to do a new text project. And it's going to be C++. And I'll go ahead and name this one like I named the others. I'll call it Eric. This is Unit 7. And I guess this is Activity 1. So I'll name it U7A1, just so I can kind of keep track of things. And I'll just save that. And I'll go ahead and fill out this header here. Oh. Oh, press the wrong button there. And I guess for project, I'm just going to say turn investigation for my description here. Okay. So I'm going to save this in a different slot so I won't overwrite my other codes. And the first thing we want to do is we want to go ahead and set up our motors. So we're going to add a device. We're going to pick a motor in port 1. We'll do our left motor. And I think we did decide we had to reverse that motor. And then we'll also add a right motor in port 10. We'll call it right motor. And we'll leave that normal. And I think that's all we'll need.
Okay, hold on just a second. You're going a little bit too fast for me. I'm sorry.
No, that's fine. Okay, so once again, and I can do that.
Okay, I didn't get to where you said the C++. How do I get that again?
Okay, so you click on File.
Okay.
And then New Text Project, and then pick C++.
There we go. Okay. All right.
Okay, and once you've done that, you can go ahead and name it something up here, by clicking right here.
Okay.
I just named it with my first name and then U7A1 since it's Unit 7 Activity 1. But you can use whatever naming convention that makes sense to you.
That's good. Okay.
And so after I named it something and saved it, I also went ahead and filled out this header information. Just put my name and the date in. And then now we're going to add our motors in.
Okay.
So to add the motors, we're going to click on this.
Add device.
Yep, add device. And we're going to pick out the motor. And we'll do port 1. And that will be our left motor. and I'm using camel case notation for that. And we're going to reverse the left motor, because if you're using gears, you need to, if there's gears on the robot, you need to reverse it. If your robot doesn't have gears, like if you just have the motor directly to the wheel, you want to reverse the right motor. Not so it just depends on how your robot is built. Since my robot has gears, I'm going to reverse the left motor. And then we'll add another motor in port 10, and that will be our right motor. And I'm not going to reverse that one.
Okay, how do you?
How do you reverse the
Yeah,
motor?
I got it. I'll remember now. Okay.
So when we're doing this when we're doing this investigation, we're going to be changing the time a lot, because we're going to be constantly tweaking that time until we get that 90-degree turn in, and then we got to do the same thing, but speed it for 100 RPM. And so it would probably be good if we made some variables. We can make a variable for the speed and a variable for the time, kind of like what we did with one of the programs yesterday. In fact, we could just like open up that program yesterday, and all we would really need to do is change one of the forwards to a reverse, and we would be fine. But we're going to just write it from scratch today. So what I'm going to go ahead and do is I'm going to put some comments in. So what I want to do is, what am I trying to do? So above the main, that's where I'm going to have my variables. So I'm going to make a comment, declare variables. And then in the code I'm writing, though we did see a different way that we could use spin, where we could set the speed and the spin. We're just going to use that set velocity command this time. So I'm going to be setting velocities, and then I'm going to perform the turn. So those are the things that I want to do, and so I'm going to have some comments just telling me what I do, what I'm going to be doing there. So Sandra, is that good so far, or?
Yeah, I'm working on it.
Okay, I'll just.
Since this is a 90-degree turn, would you specify in the comments like what kind of turn you're trying to do?
Well, normally yes, but in this case, because I'll be using this same code to do both a 90-degree and a 45-degree and a
Gotcha.
180-degree, and I wouldn't want to have to change the comment every time that I'm changing the turn.
Makes sense.
So in this case, I'm just going to keep it kind of general there. Also, I believe we're investigating both swing turns and point turns in this assignment. Let me take a look at that. No, yeah, because we're going to do swing turns and then we're going to do point turns. Yeah. And honestly, the values we the values we calculated was for a point turn. Didn't really do it for a swing turn. But let's see. So for a swing turn, the point of rotation is going to probably be typically you would kind of like measure from like the back wheel, like maybe from the back wheel to the front wheel. That's a little trickier to say, but so in our case, we're just really trying to get to the ballpark here. Um, and actually, at this point, well, so we haven't actually introduced that yet, as far as like doing the math on that. So this first time, they're probably just going to take a guess at what it should be, and then try to narrow it down from there.
Okay, I don't know if I'm correct on this, but like, okay, so say if your robot was pretty much a square and you were
Mhm.
doing a swing turn, would the rotational point basically be like in the cross section of that? Would the point of rotation be in the cross section of that, or do I have that wrong?
Pretty much like you can measure the diagonal from one wheel to another, and that
Yeah.
should be pretty close. Yeah,
Okay, that's what I was thinking, but I wasn't quite sure.
yeah, yeah. And there's there's a lot of it's kind of, especially with a four-wheel drive, it is kind of weird because like we're because there's actually two wheels that are kind of providing that turning torque, and so it's like you kind of would take like the average between those in a way. Um, so, but we're just worrying about approximates here. Now, in our case, we can pretty much because when I was measuring that, it was a little under 10 inches, which our original radius was 5 inches. So really, we can just kind of double what we had, and that would kind of give us a good. Because so instead of 0.875 seconds, we'll just double that for our swing turn, and that should give us kind of an approximation of where we should be. So, 1.75 seconds is what we're going to be shooting for our swing turn. Okay. Um, are we ready to move on?
Yes, I'm caught up.
Okay. So we're going to go ahead and declare our variables. So we're going, and these are numbers that we're going to just change. So, and we're going to need two variables because we want to kind of control the speed, and we want to control the time it takes to turn. So we're gonna okay. So in our case of our time, since it's got a decimal number in our time, we probably don't want to declare that as an integer. So instead, we're going to declare that one as a float. So a float is a decimal number that we can use. So we're going to say float, and I guess we can just call it, how about call it turn time? Does that sound like a good name?
Good with me.
Okay. So we'll say float turn time, and we're going to set that to 1.75 because that's how many seconds that we're going to want it to turn. And then our second variable is going to be our speed. And we're going to be setting that to either 50 or 100. So we can leave that as an integer because that's just going to be a whole number. And we could just call that speed. I think speed's not taken, so we can just call it speed. And we'll set this first time to 50, and later we'll change it to 100. So those are going to be the two variables we're going to make. We'll have a turn time and we'll have a speed. So yesterday, one of the things we talked about yesterday were our different types of variables. And so int stands for an integer. An integer is whole numbers, and they can be positive or negative, but they can't have any decimal points in them. The next type of number we talked about were floats. I think floats can have up to 7 sig figs in them, and they can be decimals. So if anytime you want to use a decimal, it can't be an integer. You have to make it a float. If 7 sig figs isn't enough for your number, there's also what's called a double, which a double can hold basically twice as many sig figs, a little more than that. If you need a much longer number. And then if we're trying to store something like, instead of storing a number, if we're trying to like store like a single character, there's the char for character. Or if we're trying to store like a lot of text, like maybe a few words or a sentence or even just one word, it would be called a string, like a string of characters. And then if we were just trying to store like a true or false, we would use bool, B-O-O-L, for Boolean. And that's for any time we're storing a true or false. So those are some of the more common variable types. But in particular, you'll be mostly using integers or floats. So int or float.
Okay.
Okay. And so we've made our variables. So let's write our code for setting our velocities. So you might remember we just used the command set velocity. So we're going to say set left motor, set velocity. Now, if you don't want to type it out yourself, you can also pick these as you type. And you might remember we need to set the number for that set velocity. But since we have it stored in this variable speed, we're just going to say speed here. And then it's going to be in percent. So when we typed out speed here, it's going to be like, oh, well, what's speed? And then it's going to come up here and say, okay, well, we said speed is 50. So it's going to, so anywhere where I say speed, it's going to think that's 50. And then if I were to later change the speed to like say 100, then it would look for speed and say, oh, it's 100. So I'll use 100 for speed. So we're going to do the same thing for right motor. And once again, you can also just drag these in too. So like if you go up to motion here, you can default to the first motor. So that's why every time I drag it over, it's staying left motor. So I would need to change that left motor to right motor. And I'm going to change that 50 to speed. So we've set our speeds. Now we have to just do the turn. Now I'm going to go ahead and write this for a point turn and not for a swing turn. And I'll explain why in a second. But we're just going to write this for a point turn. And for a point turn, it didn't really specify which direction we need to turn, but do you guys have a preference there?
I have no idea. I'm gonna be honest. I'm still doing the.
I already did mine for right if y'all just want to do right.
Okay, so right's always right, right? So we'll do a right turn.
Left-handed.
Okay, so in order to do a right turn, that means the left has to go backwards and the right has to go forwards, right? Because then it'll turn right.
Other way around, isn't it?
No, yeah.
Left needs to
Okay.
go forward,
Yeah,
right?
yeah. Left needs to go forwards. Right needs to go backwards. Yes.
Wait, in a point turn though, aren't we? Are we doing point or swing first?
I'm going to write this for a point turn.
So isn't that the one where one's on and one's off though, or am I getting that backwards?
That's a swing turn.
Okay, that's swing. Okay,
Yep.
gotcha.
Okay. But I'm going to go ahead and write this for a point turn. So for a point turn, like you said, we want our our left motor to be forward and our right motor to be backwards. So what we're going to do is we're going to say left motor dot spin, and we're going to say forward for it. And then we're going to do our right motor dot spin, and we'll do reverse for it.
May I interject something real quick?
Yes.
So maybe an easy way for you to remember which way or which one is which is a point turn is a rotation around the central point, and a swing turn is a revolution around that central point. Does that make sense? So one's a rotation, one's a revolution, basically.
Yeah.
Yep. Or, a point turn, both sides are moving, and a swing turn, only one side's moving. I mean, and also there are, like I said before, there are a lot of ways you can do a swing turn. Another way you could do a swing turn is instead of one side going forward and the other side not moving, you can have one side go in reverse and do like a reverse swing turn, and that would still be a swing turn. Or as I mentioned before, you could actually have them going at different speeds, and that would be like a wide radius swing turn. But at that point, with if both sides are moving, then your center of rotation is actually outside your robot, outside the footprint of the robot in that case. So if you want to make a really wide turn. But at any rate, back to this. So we're going to spin the left motor forward and the right motor reverse. Then we just need to wait for a certain amount of time. So we'll wait, and that's where our turn time variable comes in. So we're going to wait turn time seconds. And then finally, we need to stop the motors. So we're going to have a left motor stop and a right motor stop. Now, I wrote this for the point turn, right? But the very first thing it's asking us to do in the exercise is do a swing turn. But a swing turn, we're just going to run the left motor. So what we can do is we can just comment out the line for the right motor. And now we're going to do a swing turn. And we don't even have to bother commenting out the line for the stop because, it's not going to move anyway. So that's not going to affect anything. So now we can use this for our swing turns. And what we would do is, we would, and I wrote all this and I was not checking as I went because I was so confident that I got everything right that I knew I wasn't going to have any errors anyways. So that's why I didn't check. But normally I would. I would be checking as I go along, just hitting that build to make sure I didn't have any errors along the way. But there's our code that we would use for this investigation. And so we would download this, and I would use the joystick for this, or the controller for this. I would download the code through the controller, and then you would have one person kind of setting it up, make sure it starts off right parallel with your line. and then we would run this, and hopefully, if we got it right the first try, when it turns, it would just do a 90-degree turn, and so the side would be parallel with our line. But if it's off a little bit, if it's not quite parallel, we would need to start playing with this turn time number. So we would play with this number until we got it dialed in, and we had our 90-degree turn. Um, and so and also so we would dial it in and get our 90-degree turn at a speed of 50, and then we would put down our time for that, and then we would change the speed from 50 to 100, and then probably once we dialed in 50, we would probably start by cutting that turn time in half for 100. Because that would be a good place to start with. And then we would dial that down again until we got our 90-degree turn for our 100, our speed of 100. And we record that here. And then now that we have those measured times for doing a 90-degree turn with a 50% power and a 90-degree turn at 100% power, then we can make our predictions for a 45-degree turn. So our predicted time should be half of for a 45-degree turn.
Half a
Yeah, it would
90.
be it'd be half of what we have for our 90-degree turn. In the same way, our predicted for our 180-degree turn should be
Double.
twice, double. But then we would actually we would start with our predicted numbers. We would put those in, but then once again we would dial it in until we hit that perfect 90 or that perfect 45 and that perfect 180. And that's what we would record as our measured times. And then once again we would calculate the percent error between the two.
Do you have them like in their engineering notebooks, like once they have it dialed in for a certain robot, like make like a little like chart in their engineering notebooks, like if you need this turn, use this set to begin with? Like so it's like the best that they can like probably get to, and then so they don't have to do as much tweaking.
Yeah. Since they're usually recording all this in their engineering notebooks anyways, I usually tell them to refer to this again. And typically the only turn I think the only turns they're really going to be doing mostly is 90-degree turns. So these values right here, but I usually and it wouldn't be a bad idea for them to definitely like highlight this part and star it so that they can refer back to it. But yeah, that's kind of what we're going for. So if they wanted to, like you said, put it like as a separate note, then that would be good too. Of course, once again, that's only going to apply to whatever gear ratios you're using, and
Right, true.
and also any sort of difference in weight distribution, like say if you added like a different arm or something like that, or it's going to be a little different when it's carrying something too, because that's going to change the weight distribution. That will affect it slightly as well. So, so those are all kind of things you have to keep in mind. But when we use encoders, that won't be an issue anymore at all. So when we do 7.3, where we're actually using encoders, we won't have to worry about that anymore, because we're just going to have the robot turn until the motor is turned so far. And it doesn't matter if it takes a long time or a short time. When we're using encoders, we won't have to worry about these variances. So it's going to make it much more consistent. Okay, so we're going to do all that for a swing turn. And then we'll do it all again for the point turn. But we can use this same code. But when it's time to do the point turn, then we can just remove this comment here so that the compiler reads that line again. And now this code's back to running it as a point turn. And so that is basically what they're going to be doing for this turn investigation. So they'll have a simple code like this. Now, also, if they wanted to, they didn't have to use the set velocity commands. We could have done that in the spin like we did before, right? So we could have like said forward, comma, speed, comma, percent. And we could have done our we could have adjusted our speeds that way if we wanted to. And so that's how that activity 1 will go. Any questions about that? How does that make a lot of sense, Sandra? Or
I guess so. I've got a lot of errors on mine, so I'm still working on it.
oh, okay. Do you want to share your screen and we'll try to help you fix them?
All right, sure.
This is another one that we might want to add a wait time at the beginning too, huh?
Yeah. We could probably just do that as a standard practice for most of this stuff. So
Share. There it goes.
though actually I don't know if you would want to wait if you're running it from the joystick. Then I mean you'll be starting and stopping it from the laptop anyways. So maybe you don't want to put a wait time.
Yeah, that's a good point.
I think I might have clicked off of it on accident.
Oh,
What was it? Code
v5.vex.com. Yep.
Did it save it? You think it should have saved it though, right?
Yeah, so you might have to do file and open.
Okay. Maybe it's this one.
Yeah, click save changes. Yep.
Okay.
Okay. Okay, so first off, on line 83,
Okay.
you're missing a semicolon on the end.
Oh, okay.
Okay. I don't think you're gonna have a problem with line 88. Once we fix the other problems.
Okay.
And also go into your devices and look how you have left motor spelled. Like, yeah. Left motor. Oh, line 92. You also need a semicolon on the end of line 92.
Okay.
And a semicolon on the end of line 96. Try compiling it again. What else is wrong with it?
I tried retyping it.
Okay. On line 86 at main. Do you see how you open brace, but then you immediately close it? You don't want to close it yet. Yep.
Like that?
Yep.
Okay. Let's try it again. Oh,
Okay.
thank you, Jesus.
So now notice that the compiler didn't point that out, right? It was
Right.
pointing out all these other errors, but that wasn't actually the error. So the compiler is not always going to be perfect in that.
Okay.
No. Because from the compiler's point of view, there's nothing wrong with having a blank, like nothing inside int main. But it was a problem that there was all this stuff that was outside int main, and so it was then all of that was wrong. But yeah. Okay, so so once again, when you're running this, Sandra, you would load this on your robot, but probably through the controller,
Yes.
and then basically you would be tweaking those numbers for the variable until you hit that 90-degree turn, and then you got that nailed down, and then you would change the speed to 100, and you would tweak those variables until you hit a 90-degree turn again.
Okay.
And then
So I'd go up here and change that to 100.
mhm.
Okay.
And then you would do the same thing, but try to hit a 45-degree turn. So you would mess with your time numbers until you hit a 45-degree turn. And then you mess with your time numbers until you hit like a 180-degree turn. So a full turning backwards. And then you would repeat the process, but with a point turn. And to do the point turn, that's where you want your right motor to spin reverse. So you would just remove those comments on line 97
Okay.
to do your point turn.
Now, would the kids want to run like both turns back to back? Because I'm assuming the way that it's written now, the robot would perform the point turn and then simultaneously right after that perform the swing turn.
Well, the way it's written right now, the way she currently has it, it's just going to do a swing turn
Okay.
because only the left motor is going to spin, the right motor is not going to spin because she's got the right motor commented out.
Okay, right. So, but like in mine, like I did the code like when we were just practicing. I got the code for the point turn, but I didn't delete it, so I'd have to go back and like just take that one out.
No, do you want to share?
Yeah.
Stop sharing mine.
Let's see. Just have to figure out how to do this. Can you see it?
Yes.
So you okay? So yeah, you're doing both, but you probably wouldn't.
Right,
Yeah,
right.
yeah.
So
You
I was just
wouldn't.
like practicing it, but like I would have deleted whichever turn I was like using at the time. That's like I'd have to take out the other one.
You
Yeah,
just comment
and,
it out. That way you don't have to delete everything.
Right.
Yeah.
Oh, that's true.
and this is where you could
So
use a
just go
block,
put little like slash marks on these and
or
make.
or you could do
Slash
that block
star.
comment. So it's like a slash star and then star slash.
Oh yeah, that's true. Cool. Awesome.
Yeah. But yeah, so that yeah, you can definitely do it that way too. And that's one neat thing about coding is there's so many ways you can do things. Okay, and so um, and so the other assignment in this part of the lesson is where they have to go around an object, and once again, um, I just put tape marks on the floor, and you don't want it to be too narrow. You don't want to be too wide either, but you want to give them enough play so that they can. So if it's like slightly off task, it'll still not cross the lines. I find since these robots are approximately about 15 inches wide, kind of looks like. Or yeah, they're about 14 or 15 inches wide there. Um, 5, 10, 15. Oh, yeah. They're 15. 5, 10, 15, 20, 25. No, 25. That's 12 and a half inches wide. Well, with the gears, yeah. Yes. Well, inches wide. So fine, that's plenty of space for them. And like I said, with my squares, I just mark off a center square and then go 2 feet and mark off in every direction and mark off a 5 by 5 square. And then basically they just need to they'll they'll place their robot down in one corner, and then they just need to go forward and turn and go forward again and turn and and complete it. So the distance they need to travel is not if for instance if it's set up as a 5 foot square, the distance that they need to travel is not 5 feet though, right? Because you can kind of think of it as measuring from like say the middle of the robot to the middle of the robot. That would be the distance they would need to travel. So it would actually the distance they would really want the robot to travel would be more like 3 feet going forward. And then they would want to do a 90-degree turn, but since in the last activity they dialed in what their 90-degree turn is, that shouldn't be a problem for them. So so what you could have them do is do the math for going 3 feet forward to figure out how much time it's going to take. And basically, you would write, and I haven't been sharing this whole time, and I've been looking at this document here. Sorry about that. So, as I'm explaining this, so basically, you would have your robot kind of start here, and then it's going to go to here, and then it's going to turn 90 degrees, and then go to here, and so um, if this were like 5 feet, really it's only going to be traveling 3 feet. Because if it traveled the full 5 feet, that would be like from here to here, and that would definitely be crossing the line. So they want to stay inside the lines. So the students can do the math to figure out like how much time it's going to take for them to go 3 feet, and they can just go around the object. Now, if you don't have as much room, like 5 feet of space, like a 5 by 5 square is kind of a lot. You can just put an object, like a smaller object, like a Coke can, and then have like a shorter radius there for them to go. Um, one one year, I actually had a kid do this assignment, and instead of doing like going forward and doing a point turn, he actually kind of figured out like a swing turn. Well, he figured out the speeds he needed the two wheels to turn so that it circumscribed or so it just did a circle. Like he just kind of started here facing this way and it just did a circle around the object and he was able to like keep it inside with it just um, without really doing uh, any other adjustments at all. It just kind of just went around in a smooth circle and still fit inside. And I thought that was kind of neat. They was able to pull that off. And all that involved was just setting the left motor and right motor at the right speed in order to pull off that turn. And that was kind of neat. But it wasn't exactly what the purpose of the assignment was, but I mean but he accomplished the task, so I had to give him a kudos for that. Um, but but like I said before, so how would you write this code if you were trying to pull this off?
Are we
So,
using loops yet?
No, not yet.
so your first thing would be to what? Or wait, is this one doing it all at the same speed?
Yes.
Okay, so first you probably set your velocity
Okay.
if you're going to use the same speed for the whole entire deal.
Yeah. Sure.
Okay. And then you would want to turn both your motors on to go a certain distance, and you'd have to calculate the time to input into your code to get you to that distance.
Okay.
Anybody else? Anybody else want to add on?
Well, I mean, personally, I would do a point turn at that point, um, to the right. In this case, if I'm going up from where it says PVC, we follow that distance that you just talked about. I'll do a point turn at that top left corner, and then I would do the same formula that you already used. So basically, at that point, I would copy and paste my program, and I would do it to the right. Then I would do it, copy and paste again, both the point turn and the travel distance.
Yeah. Um, yeah, and this one's basically a lot of copy and pasting, right? So like you said before, they would just go forward a certain distance and then turn to do their 90-degree turn. And then you could just copy that 3 more times, like the code for that 3 more times, and that would complete it. So it's relatively straightforward there. Um,
How many of your kids actually get that on the first try? Like to where
no,
they've written the code and it's actually like within the margins of your taped out.
I won't say it never happens. Um, because once again, they'll have that 90-degree turn dialed in from the last assignment.
Mm-hmm.
So it's at that point, it's just a matter of making sure that that forward part, if they have to write calculations for that, but they can go back and kind of look at their calculations from like the earlier assignments, like the basketball drill and stuff, to kind of get an idea of what that needs to be. So it does happen on occasion that they nail it on the first try.
Cool.
Yep. Yep. But this is relatively simple to do. So, in fact, we can actually modify this code to do it if we wanted to. So we could use what we have written here as a starting point, and just make some slight tweaks to it. How about we do that? And we'll just kind of. So how would I take this code and change it into the one to do the century? Well, one thing I would probably do is I would add a new variable for a I'm going to call it straight time, for the time for going straight. And I would probably do the math on that and see what that is. So if we started with 3 feet or 36 inches, let me just do that real quick. 36 divided by 4 pi. Divided by 100 and times 60. And then time, since I'm using that gear ratio, times 7/3. So I got about 4 seconds. I got like 4.013 seconds. So we might just go with 4 here. And so now what we would probably want to do is we could keep the set velocity stuff, we could keep the turn stuff, and all we would need to do, of course, since this is a point turn, that turn time would be about half that. But it would be whatever like you figured out the last time. But in between setting our velocities, performing the turn, we would just have a go straight part, right? I guess we could be more specific here. And literally, we could just copy this stuff. Because going straight is kind of like a point turn, except for both motors are going in the same direction. And instead of doing a turn time here, we'll do a straight time. And let's check that. So no errors. So what we have here is we'll be going straight, and then we'll do our turn. I guess I can now be specific about the turn. Perform a 90-degree point turn. Right. Our right point turn. So that would do one of our legs of going around the object. And then I could just take all this and copy it 3 more times. 2, 3. Yep. And let's see if that's right. So we'll go straight, we'll turn once, we'll go straight, turn twice, go straight, turn 3 times, go straight, turn 4 times. Yeah. And that should take us back to where we started. So this code doesn't look pretty because it's 150 lines of code. And as Josh was mentioning, if we had access to loops, we could make this a lot cleaner. But this does get the job done.
And then if you want to do the bonus, you'd have to copy it, put everything in reverse.
Yes. Yep. So once again, it's all about thinking about the pieces and arranging the pieces of your code. Although this looks like it might be a difficult assignment, it's actually relatively straightforward as long as they kind of get the ideas. If they and that's what they should be kind of seeing, is that they use the pieces and the skills that they've developed in the earlier activities and can apply them to more complex behaviors, right? Okay, so that's turning based on time. So now let's move on, and before I move on, any other questions about either of these assignments? Like Sandra, do you have anything you want to ask, or?
I wouldn't know what to ask, but I'm good.
Okay. I would wholeheartedly recommend you actually load this code on your robots and try it out, simply because I think you get a better feel for it than, like, with me explaining it and you imagine in your head, it might not be the same as what actually happened. But if you load it on your robot and run it, you'll kind of get an idea of what we've been talking about a little better. so um, so now we're going to be talking about the encoders. So an encoders is one of our types of sensors, and it's a sensor that's built into the motors. The motors actually have a lot of different sensors in it. In addition to the encoders, it also has like a temperature sensor, so it knows if it's overheating. And in fact, when it does start to overheat, it'll actually cut the power to the motor so it doesn't burn out, and it will do that automatically, um, which is different from the older motors we used to have. Because those, well, the old, I don't know if you ever messed with the older equipment, but the older motors didn't have an encoder on them, so it couldn't keep up accounts. It was kind of dumb, and it really only had two wires, and you just ran a DC. So you could literally like kind of bend the prongs bit, and you can like just press it against like say the tabs of like a 9-volt battery to run it if you wanted to, um or those the old batteries were kind of dumb batteries too, so you could actually like directly run the motor just by touching it to the battery terminals, with the old one, um, with the older motors. um, so they didn't have like all these extra things in them. So, at any rate, so this is like a cutout of what the motors look like. We went over this earlier, but here is where that encoder is, and basically it's a little disc that has a lot of holes in it. And if you have like a broken motor that's burned out, you could always take one apart to show to the kids what it actually looks like inside, and they'll see it's just like a little white plastic disc with holes in it, and and then it just kind of the light shines in between, and the detector picks it up. And so, and it can count how many times the light shines through. And so by counting that, it knows how many times the motor's turned. So, so that's pretty neat. So once again, here's a review of our different types of variables that we went over yesterday. So integers store whole numbers. So int is for integer, and so it'll store whole number values. And those can be positive or negative. Float will store decimal numbers, and it can hold up to 7 sig figs of numbers. Doubles can also store decimal numbers, but that's if you need even more digits. So it can store up to 16 sig figs of digits. Strings are if you want to store like full phrases or words or things like that. So so if I wanted to store like a sentence or a word or something like that, I would store it as a string. So for instance, if I had like a bunch of different things that I would want to say on my brain screen, then I can store those things as strings, and then I can call on those variables later to just display that whole thing. And then characters are if we just want to store single characters. And booleans, that would be true false values. And those are also represented as like ones or zeros. So true would be 1 and false would be 0. Um, so those are our different types that we have. I bet that was Josh, right? Yep, it was
That's
Josh.
me. I'm on a hard line internet too.
Yeah, is it your firewall that's cutting out or
I have no idea. It doesn't matter what computer I use or anybody else uses. For whatever reason, our internet will get messed up at some point. I think maybe it's because we're at the end of the line and we go through like 4 to get to us. I don't know, but by the time it gets to the high school, the internet is absolutely garbage.
Well, I'm sorry for Josh. Would would hooking up to your hotspot be better on your phone? Or
I don't know.
but that would eat through all your
Possible.
data. Yeah. Um, okay, so how do we use the encoders? Well, we have another command we can use. So instead of just saying motor.spin, we can say motor.spin4. And then we feed it two parameters. We feed it the number of rotations or number of degrees we want, and then what units that will be in. And those units can either be degrees or turns. So 360 degrees would be the same as one turn. Um, and so so that's going to come in handy. So now one thing about encoders is when you use that spin 4 command, it's going to spin until it hits the right number of turns or the right number of degrees. However, it will the program will run everything one at a time. And so normally what will happen is if you do this, use the spin 4 command and do a right motor and then do a left motor spin 4, it will wait until the right motor is finished turning its turns before it does the right motor, before it does the left motor. So if you want both motors to run at the same time, you also have to use this additional false here. And what this false does is it tells the motor to not wait around to finish, just go ahead and move on to the next thing while this is going on. So anytime you want to run multiple motors at the same time, that first motor needs to have this false here. If you don't have that false, what will happen is the right motor will run for 3.25 turns, and then the left motor will run for 3.25 turns. So, like if you were trying to go forward, instead what would happen is it would kind of do like a swing turn and then do another swing turn the other way.
And
So
then you're right back where you started.
well, kind of. It kind of more almost like kind of like an army crawl.
But you're not forward, is what I'm trying to say.
Yeah. But yeah. So so if you want both motors to run at the same time, when you're using spin 4, you have to put this false in.
So would you, like at the very end of the last lesson, beginning of this lesson, prior to showing them the slides, would you show them that, how it would army crawl if you did it using the spin 4? So like you as the teacher have your robot set up and then you show them doing it?
Yeah, and that's something you can introduce like mid lesson. For instance, if you wanted to, like when you got to this slide, if you want to have like a program preloaded, you could show like this is what it looks like without the false in there, and this is what it looks like with the false. Or you could have the kids whip up that program real quick too, if you wanted to. Because
Yeah, that's
really,
that's kind of what I was thinking of, is to have them get annoyed because it's
just
army crawling, and then, well, what do we do? And then you like watch this, boom, and then show them the slide, and then
You're
it's
like,
like
how'd
magic.
you do
Fix that
that?
real quick. Yeah.
yeah. In that case, what you may want to do is move this slide till later on. uh, is that all there is? This slide. Well, it's kind of introduces that idea. Well, or you could, or like I guess after you've introduced the spin 4, but before you get to this slide, um, you could maybe say, hey, let's try this out, and then like have them write a right motor spin 4 and a left motor spin 4, and then and you can say, well, let's go for like 10 turns and let's see how far it goes. or something like that. And yeah, and then they would run into that problem, right? But yeah, and I guess the place to introduce that would be before you got to this slide, but maybe after you introduce the spin for command.
Yeah, so just
Oh,
right
yeah.
there, boom, do it real
Yeah.
quick, and then okay.
Yep.
Anything that makes you feel smart in front of the kids is always a winner where they're like, how'd you do that? And you're like, watch this.
Well, and I mean, for me, it's more of I want to make them mad, and not like mad, but make them
No, yeah. So
confused.
they
Like, why
don't
did that
repeat
just
this.
what just happened? And then we can go through and explain what just happened, and explain like you just mentioned to us that the codes are going to follow a line, and so since this comes before this, then you have to make it where they're simultaneous. And now, boom, here's how you do that.
Yep. And in a lot of ways, it's kind of like science, like with a discrepant event, to get them thinking about things like this is what we were expecting to happen, but this is what actually happened, and here's why. Yep. Yeah. So, but moving on, because we still have a good bit to talk about. So also you can say the direction as well. So if you don't put the direction, it's going to assume forward. Well, actually, that's not true necessarily. Okay. So, but you can say reverse if you want to go reverse, and you can also say forward if you want to go forward, but you don't have to say forward. But if it's a positive number, okay, well, since you're telling it reverse and then a positive number, it will be reverse. If you didn't have the reverse here and it's a positive number, it will go forward. But you can, instead of saying reverse, you can just put in a negative number. And if it's got a negative number, it will go backwards. So these are two different ways of making it go in reverse. You can either say reverse, or you can just give it a negative number of degrees or rotations to turn, and it will go in reverse. By the way, similarly, that's also true of the set velocity command, and also when you're doing the spin for command, and if you say a negative speed, and not spin for, but just a regular spin command, and if you're doing the speed, if you set a negative speed, it will go backwards. So in this case, so these are different ways you can make it go in reverse. You can either just say reverse, or you could give it a negative. And obviously, if he had both reverse and a negative, then that would be two negatives, and it would be back positive again. So, so if he said reverse negative 500, then that's actually going to go forward. And just like with what we were doing earlier, like with weights and stuff like that, we can always use variables for that as well. So like in this case, we use the variable dist for our distance. And so, by the way, if we were to do this, what would happen? What would our robot do if we were to put this in?
Does the false and the negative cancel each other or not?
No. Remember, once again, the false just tells it to run both
Wait.
lines at the same time.
Point turn to the
good.
right.
Yeah, we would do a right point turn. That's right. Because our right motor would be going backwards and our left motor would be going forwards. And so it would do a right point turn. That's right. Yep. And then we can also do any sort of math in here if we wanted to. So if we wanted to go 1,000, we could just say dist times 2, and that would be 500 times 2. And we could do like any sort of math in here to get our number if we wanted to. So that would be handy, like for with like say the basketball drill, for instance. We can just do our whatever variable we had for our 2 feet distance. And then for 4 feet, we could just say that times 2. So What's actually going on when you're running this? So at this point, we can introduce flowcharts to them. They'll also see flowcharts in the engineering class, and if they're taking both the engineering class and robotics, hopefully by this point they've also, or maybe being introduced to a flowchart as well. So, are you guys familiar with flowcharts?
Yes.
Yeah.
Okay, so I hear 2 yeses,
A little,
a little. Okay,
not fluent, but a little.
yeah. So a flow chart. Typically, like your start and end are usually represented with rounded boxes like this. Your actions are represented with square boxes, and then any sort of decision that needs to be made is represented with a diamond. And so, if we look at this flow chart right here, this is a flow chart for, like, say, if we follow this. So let's say we have a touch sensor or like a button on a robot, and it's saying if that button's being pressed, if it's not being pressed, we're going to run our motors, and then we're going to loop back around and check again and see if it's being pressed. If it is being pressed, we're going to stop our motors and then end the program. So this would be the flow chart for a loop. And in this loop, this would be like basically telling the robot to run forward until the button's pressed. So like
So
if you have,
this would be like to see it, like to help the robot like not run into a wall.
yeah, or to stop after it's run into a wall and not keep running into the wall. Yep.
Right. Gotcha.
Yep. So that's what this would do. It would run forward until the bumper was pressed, and then it would stop and end the program. Yep.
So this is creating the if-then statements?
Uh
Or
yeah,
the
well, in
beginning
this
of it, I
case,
guess.
this is a loop right here. So this would be like a while loop, like while the button's not pressed, and we're going to run these motors. And then once that's no longer true, we'll break out of the loop and stop the motors. So like if you ever see a flow chart and it goes back in on itself, then you know you're dealing with a loop. So the reason why we're introducing that is because that's kind of what's going on with these motor encoders. So, or when we're using the spin 4 command. So let's say we told it the right motor spin for, like, say 500 degrees. So basically what's going on in that line of code is it's really a loop. And what it's doing is it's checking the value of the encoder, and it's checking, well, have I hit less than 500 degrees yet? If I am still less than 500 degrees, then I'll continue to drive forward. But if I'm not less than 500 degrees, well, so that means I've hit 500 degrees or I'm even over 500 degrees, then I'm going to break out that loop and stop my motor. So that's actually what's going on when we say spin for like 500 degrees. It's actually performing a loop where it's checking that over and over again. Have I hit 500 yet? Have I hit 500 yet? Over and over again, and then finally, or am I over 500 yet? Or am I still under 500? It's going to say that, and then if I'm no longer under 500, then it's going to break out and stop the motors and end that line of code. So that's what's going on with those encoders.
Now it's doing that it's doing that continuously through that command that you just wrote in that previous slide.
That's right.
Okay.
Yep.
So
It's
that's
just,
nothing that you're having to program. That's a loop that's already embedded in the encoder.
that's right.
Okay.
It's well, not embedded in the encoder. It's embedded in that spin 4 command. Like if you were to, because that spin 4 command is a function, and if you were to open up that function, there would be like other code in that function, and that's basically what's going on inside that function there.
Gotcha.
Yep. So yep. So this is what's kind of happening under the hood when you're using that spin 4 command. So what are the benefits of encoders? Well, the biggest benefit is your distance that it's going to travel. It doesn't matter the velocity. So it doesn't matter if you're going 50% or 100% or 25%. It's just going to go until it reaches that target number of rotations. And it doesn't matter if it's going faster or slower. So and that's a really big advantage over like doing it by time, because like if the robot's going faster or slower, that will affect how far the robot goes. And so because of that, it's much easier to specify a distance you want to travel than it is than calculating the time you needed to travel. And Josh had brought this up before, but this also kind of eliminates the problems with power inconsistencies, because as Josh had mentioned, I don't remember what day it was, but he did mention this before. If your battery is lower, gets lower, then it does have a lower voltage there. Now these batteries are designed to kind of keep kind of a steady voltage, and just if it gets to a low voltage, it just won't provide power anymore to keep it consistent. But you still will have a little bit of voltage drop off with these. So, but that doesn't matter anymore, because even if the battery was running low, it's still going to just go until it hits that encoder value, whether it's going slower or faster. And so once again, we might remember distance traveled is going to be the distance that one revolution travels, or in other words, the circumference of the wheel times the number of revolutions we do. So, so if we turn for like say 5.66 turns, and we have like a 4-inch wheel, then the distance the robot's going to travel is 5.66 times 4 pi times the circumference. And so that's how far the robot would go. And so typically when we're commenting these, we also want to kind of say like what our target distance we're trying to go. So maybe we're trying to go 20 inches. I don't know. It doesn't really say what wheel size it has, so I don't know if that would work out. Probably that doesn't work out with a 4-inch wheel, but maybe that works out with a different wheel size. But anyway, so when you comment this, you'll probably want to say what you're intending to do. So that way, if it's not working out, you can look at the comments like, well, I'm trying to go 20 inches, but when I'm running this, it's not quite going 20 inches. Maybe I need to adjust these numbers a bit. So for instance, here's a simple problem here. So if you want your robot to travel 20 inches, how many degrees does your robot make to travel a distance if your wheel diameter is only 1.125 inches? That's a tiny wheel. I think that's a Lego wheel, isn't it? Because that looks like a Lego axle to me.
And maybe.
Yep. Because that's not a square axle. That looks like one of those notch axles like that the Lego kits have. So could we figure that out? How many degrees we would go? Or how many degrees that we need to tell the motor to turn to go 20 inches? Can we set up a dimensional analysis for that?
I got like 2057.
2057. I haven't even done the math yet, and you've already got it knocked up. Let me.
Well, it's the turns from the previous example, so we know how many turns it needs to go.
Oh, okay.
I mean, well, it's not perfect, but it's really close. Because whenever I did the math on this one, it's going to be close to 5.7, which is really close to what they had, 5.66. So it's going to be around 2050-ish, I would assume.
I got something way different, but I may have missed this. Oh, you know what? Never mind. I missed a pi.
Yep.
I missed
Gotta
a
have 20 divided by 1.125 divided by pi, then times 360. Yeah, it's like you said. I got like 2038 as well. Degrees.
Yes, I also got that.
Um, this is what that setup would look like. So we started with the 20 inches, and the circumference of the wheel is 1.125 pi. And then there's 360 degrees in one rotation. So that's the numbers we kind of use for that to get the degrees. Yeah. Okay. And that just kind of run a 2040, which yeah, that would be to 3 sig figs. So if we were to run this and we were using those wheels, then we should end up traveling 20 inches. Yep. And once again, remember if we want them both to run at the same time, we got to have that false in there. Yep. So that's what we have here. Do we want to try this question, or do you think we're good on this stuff?
Can you share your screen again? Because I don't think we can
Oh,
see it.
I am sorry. Okay, so yeah. So we were looking at before. We figured out it was approximately 20-40 degrees, which would make us turn 20 inches. And then this last question says your wheel diameter is 1.125 inches. So these little tiny wheels. You want your robot to travel at 1800 degrees. How many revolutions would it take to travel 1800 degrees? Oh, that's a two-part question. So how many revolutions would it take to travel 1800 degrees? And then what would be the distance in inches it would travel? Well, to figure out the revolutions, that's really simple, right? We would just divide by 360, correct?
Yeah, it should be right.
Isn't 1800 divided by 360 like 9 or something? No, it's 5.
5.
I was way off. Okay, so it's going to do 5 rotations. And so the distance it would travel in inches would be just 5 times the circumference. So 5 times 1.125 pi. And that would give us our answers. Yep.
Which is like 17.66 inches.
Yeah. And that's what they have in the lesson notes too. So
Good, we can do math.
yay.
My phone cannot, because mine has 17.67 and it's greater than 6.7. So it must have a different decimal value for pi that it rounds out to than y'all do.
Well, that's probably true because we're probably I've been just using 3.14 in my calculations, what isn't there will be like a little bit of difference there than if you use the full value for pi, or when obviously not the full value for pi because but if you use more digits for pi. So what activities go with lesson 7.2? Let's take a look at that. Well, I went too far. So unit 7, lesson 7.2. So there is an act. Actually, I think that's just the code for that. Let me back up.
Looks like there's 2 basketball drill things.
I think one of them is just the answers for it. Yep. I think. I don't think it's 2 different assignments. Yeah, one of them is the solution for it. Let's just look at these solutions instead of going through it and writing out this code today. So once again, we can do the math, kind of like what we just did a second ago, to find like how many degrees we need to turn to go 2 feet. And then if we want to go 4 feet, we can just double whatever we got. And if we want to go 6 feet, we can triple that. And 8 feet, we can quadruple that. And we can do that. And this is one way they did it, where they just have 4 distances and they just did the numbers like that. Or and that's actually kind of how we did it, right? When Miranda was doing it yesterday. Because by having 4 different variables, that means that if it doesn't work out quite right on one of those legs, then you can kind of tweak those numbers. Now for the actual part of going forward, that's the spin for it. Instead of turning on the motors, waiting and stopping, all we need is these 2 lines of code for each one, right? So we have our right motor spin for distance 1 degrees false, and left motor spin for distance 1 degrees. And we don't need a false there. In fact, we don't want a false there because we want it to finish running before doing anything else. So that would have us going forwards. And to go backwards, we could just say negative distance 1. And that would have us going backwards there. And then to go to 4 feet, we could have either had a distance 2, like what they're doing here, or if you only had one variable, you could say that distance 1 times 2. And then to
Okay,
go,
and so I'm just trying to get this in my head. So you don't need the stop command because once it completes the rotations, it's done, so it stops anyway.
yes, because
Okay.
the spin 4 automatically has kind of a stop built into it.
Got it.
Yep. Yeah, it will stop it when it's done. Yep. So that's why we don't need to stop anymore. Yep. And so you can see that this way of doing a basketball drill is definitely much fewer lines of code. And it's a little more straightforward. So instead of having 5 lines of code for each leg, because we got to turn on both motors, wait, and then stop both motors, we only have 2 lines of code. Now, in practice, if I were personally doing this assignment, I would put a wait in between each of these. Like after it's gone forward, I would maybe wait half a second. And then after it's gone backwards, I would wait like half a second. And that's because you might run into the same issues that we had before, where going from a forward to a backwards really quickly without giving it a chance to stop first can cause a robot to kind of jerk a bit. Like it might kick up and try to do a wheelie when you do it, especially if you're going really fast. And that might throw off it going back in a straight line. I wish I was on my school computer, because I wrote a basketball drill code for this where it was kind of nice because it smoothly ramped up speed and then slowed down at the end. So
I did a practice one last night just for like practice, and I slowly amped up the speed, and it like did a nice like acceleration, like it got faster and faster, but it wasn't jerky.
mhm. So you mean for the step one, the simulated acceleration, or did you write your
No,
own smooth?
I just like wrote, I just was just playing around to just like get it all in my head. And so like I wrote a code where it went a certain number of seconds at a certain speed, and then it went a little bit longer at a certain speed and a little bit longer at the next speed. And it like transitioned really, really well.
Yeah. And that's actually not a bad idea. Now if you wanted to do that with this is much that and that's much easier to pull off with these encoders than it is with time. Like if you're trying to, for instance, if you're trying to hit a certain distance and you're constantly adjusting your speed as you're doing it, that's a little trickier to pull off, right? Um, because because the distance you go at one speed is going to be different than the distance you go at another speed. Um, and so you have to kind of keep all the speeds into account when you're determining the distance you're traveling. But with using these encoders, it doesn't really matter. Like, um, say you're trying to go 2 feet or whatever, you can maybe have the first 6 inches be at like 25% velocity, and the next 6 inches be at 50% velocity, and so forth, and then and then kind of ramp it down as you get close to it. So, and that's much easier to pull off and still hit your target distances if you wanted to be really complicated about it. Yeah, but get that smoother transition. Yeah. All
Are we
right.
ready for that smooth acceleration that we talked about yesterday?
I do want to. Yeah, I do want to introduce that for sure. But I don't think we're ready for it yet because let's make sure we go through the rest of the lesson.
Okay, I was just picking.
No, I'm excited to do it. If you guys are, smooth acceleration. Um, let's look at let's look at lesson 7.3. That's our final part of this, and this is where we're going to be turning and also using integrated encoders. Just to recap, we have our swing turns and we have our point turns. And to do a swing turn, these are all we need to do is just tell the motor to turn. So we could go ahead and set the velocity of the motor if we wanted to first. Because it only defaults to 50 RPM, not 50%, but 50 RPM. But yeah, all we need to do is just tell it how far we want to go. So in this case, we're turning forward for 3 turns. That is going to be a lot. but when we say forward 3 turns, that means the motor is turning 3 turns. That doesn't mean the robot is turning 3 turns. So you need to make sure the kids have that distinction. That's just the motor, and if it's a 1-to-1 gear ratio, that also means that's the wheel turning 3 turns, not the robot turning 3 turns. So you can just say swing turn to left, and typically you would want to say like how far that swing turn is, like swing to the left, like 90 degrees or something like that. Or so you can say like a 90-degree swing turn to the left. Now, with a point turn, you're just going to have to work both motors. And as it says here, there is a problem with this code as it's written. I guess that doesn't show until I actually run the slideshow. Yeah, if we're trying to do a point turn and we just wrote this out, what is the problem with this code?
You're missing the false, right?
That's right. If we don't put that false on that first line, what's going to happen is it's the right motor is going to spin, and then after the right motor is done spinning, the left motor will spin. So that's not what we're trying to go for. So if we want that point turn, we got to make sure we have that false on that first line. Oh, and by the way, if you had a 4-motor drive, with a 4-motor drive, you would have like a front left motor and a back left motor and a front right motor and a back right motor. And if you're trying to get them all to spin at the same time, you would have a false for the first 3 of them, and then the last one wouldn't have a false. So that way you can have all 4 motors running at the same time. So those first 3 would all have falses, and then the last one wouldn't have false. So yeah, so we got to have that false. Now, what if both of these had falses? If both of them have the falses, then it's going to start doing it, and then whatever's next in the code, it's going to also immediately start doing it too. Sometimes that can be useful. For instance, let's say you're trying to raise an arm at the same time you are going forward. Like, for instance, if you're concerned about your match autonomous in a competition and you only got 15 seconds to do everything, you don't want to say necessarily move forward, then raise your arm, and then open your claw. You might want to do a lot of those actions simultaneously. So maybe you would want a false here too. Oftentimes, that's not a great idea because you kind of want it to finish what it's doing, especially if the next thing you're doing is like if you're going forward and then doing a turn. You don't want to start going forward and then immediately start doing the turn. So here's 2 different ways we could do a left point turn. So one, we can specify the direction by saying forward or reverse. Or once again, another way to do a reverse is just do a negative number there. So going forward at -3 turns is the same as going at reverse for 3 turns. So either of these ways would be fine for a point turn. Okay, so how do we calculate how far we need to turn? This is, we went over this actually earlier than we normally do because we went over it like in 7.1 just now. But what you got to think of is that that robot is turning around basically this circle here. And this circle is kind of like where the wheels are making contact, and it's kind of following along in that circle. So if it's a 4-wheel drive like this, you can measure from the center of rotation to where the wheels are touching the ground, because that's going to be the radius of that circle. So in this case, and it turns out in most cases, if you're building a standard robot, that radius is about 5 inches. So if the radius is 5 inches, then the circumference of that whole turn is going to be 2 times the radius. So 2 times 5 times pi inches. In other words, the circumference of this circle would be 10 pi inches. And so therefore, if I wanted my robot to do a full 360-degree turn, then the target distance I'm shooting for is going to be 10 pi inches to go around a full. Now, if I only wanted to do a 90-degree turn, well, 90 degrees is a quarter of a 360-degree turn. So in that case, I would only want to go a quarter of that 10 pi inches, or 2.5 inches, 2.5 pi inches. So so when we're trying to figure out how much to turn, that's how we do it. So first, we kind of need to find the circumference of the circle that the robot is making, and then we can use that for our target distance that we're trying to travel to. Does that make sense to everybody?
Yes.
Yes.
Okay. I just don't want anyone confused on that point. So, okay, great. And so here's just some math for doing it. But once again, I like to use the dimensional analysis method of setting up the T-charts or the picket fence. So there's just some math problems for doing that. And then, so a swing turn works the same way. It's just that the difference from the center rotation to the wheel is typically longer. But it works out the same way. Okay, and that's it for these turning slides. Let's look at what the activities are for this. Yeah. So the activity for this is the same century activity that we did before, where we're turning for time. I don't have that activity pulled up now. Oh well. But where they're going around a thing in the middle and not hitting any of the walls. But the only difference is this time we're going to use the encoder, so we're going to use the spin 4 command to do all this instead of doing it based off of time, where they're using the spin command. And what they should find is this is probably a lot easier to do, and they'll probably get more consistent results out of it when they use the encoders to do this activity. So they'll be doing the same activity again. They'll still be trying to drive around an object without going outside the lines. But it's just this time they're using spin 4 and they're using the encoders instead of having everything based off of time. So just like with the doing the basketball drill again with the encoders, how it kind of cuts down on how much you have to do. They should find that using the encoders for this should be a lot easier as well. And I think that's all of. Let's lean at 7. Let me just. We're on day 5. Let me just see what all we were supposed to have done here. Yeah. So, what are the assignment tests? Do this Unit 7 activities and do the Unit 7 homework. Okay, so that's the asynchronous stuff. Okay, so what do you guys need to do? I guess, like it mentions here, we're going to do these Unit 7 activities. So, but you guys did some of them we went over most of them together. We didn't do this last century activity together. And we really just kind of looked at the solution to the basketball geography encoders, but try them out on your own and give it a shot. That's what looks like we're going to be doing now.
So are we gonna do it like the same way where we just like save the file and then
Yeah,
upload
save
it
the
to
file
Classroom?
and yes, save the file, and then when it's when it's added in Google Classroom, just upload the file.
Okay, so like we can like if we want to like do this later, like in the weekend, we can.
Yeah,
Okay,
yeah, that's fine.
okay. So as
Yeah,
long as
'cause
it's done for Monday.
yeah.
Okay.
Speaking of Monday, okay, actually, Monday is a little different in the schedule, and that it looks like the facilitators are having a morning meeting until well, what it says here is like from 8 to 11 there's a facilitator meeting. So I think you're supposed to use that. You can also use that time to work on those activities there. So like if you still want to log in at 8 and then work together on any, or like if you have any questions to each other. And then I'm supposed to join back up with you at 11 for any questions that you had with these activities. So yeah, so that's what it looks like Monday's day is just working on these activities.
So should we should we all just wait and do them together on Monday, or should we work on them on our own time? Or is that
Well,
like our choice?
that's kind of your choice. I personally would recommend at least attempting them while they're still fresh in your head.
Mm-hmm.
Because I feel like by the time Monday comes around, if you hadn't tried them at all, you might kind of, because right now it's probably clicking a bit, but I bet after a weekend it might not click as much with you. But I guess the idea would be to help each other out on your own
Okay.
on Monday. Yep.
I mean,
So that's
or we could just work on the code over the weekend, and then on Monday that could be our test time.
Oh, yeah, true.
oh, you mean going over the exam?
No, no,
I
no, no,
mean,
no, no.
Like testing it
Testing
on the
our code.
robot.
oh yeah, testing out. Yeah,
Yeah, like we could just like while it's fresh, like you said, we could do that today and then over the weekend, and then on Monday we have those built-in hours to test our robot with it if we wanted to
yeah,
do it that way, possibly.
yeah. That would be a good idea too. Um,
And we could ask each other questions.
yeah. Even though I won't be there from 8 o'clock, it would be really nice if you guys still logged in at 8. To to help each other out, because I don't know. I think I'm relatively approachable, if but you might be more comfortable asking each other questions and asking me.
Well, what if it helps, like if it helps for like everybody who's like still not like really, like I have this all the time, but like if it helps, I can Daniel should be around on Monday. So like we'll have somebody who teaches this class for like the past 10 years with us and available.
Mm.
So that's also kind of an option too.
Yeah.
And you did say that we aren't doing the where we have to go through and find a sensor and make a presentation about it, did you?
Project. Uh, no, I mean, it. She does have a kind of. She does have a listed on here to do that. I do. Do you guys see that as busy work, or it might not be busy work? Because like if you actually like researching about that sensor, you might learn some about it in that process. But I don't know. What do you guys think? Do you think you have your hands full enough with just the programming assignments?
I mean, well, how much, like, how in depth are we talking? I mean, if it's just supposed to be a poster presentation,
Right.
you
And they don't
can't
like a
go
whole lot of
overboard with
text.
it. Yeah.
Yeah, they don't like a whole
So,
lot of text either on the posters.
I mean,
Yeah.
it's like it's not going to be a terribly long assignment, but it is a little busy. But
Yeah. Um, I well, I guess it wouldn't hurt to do it. Just that way, that way when if anyone like if any of the higher ups were to look to see that you guys have completed what you need to be certified to teach this class, it wouldn't hurt to have the more work that we can have to show that, the better.
It helped that they put the things on the Google Classroom so we can add the work we've done.
Yeah, and that's that's partially my fault because I think Vanessa has expected me to be able to add that now, and I'm not. I'm just still. I just she sent me the teacher link a couple of times, but every time I click that join link as a teacher, it just sends me over as a student. Um, and so that's probably why those days assignments are in there, is because I think she wanted me to do that, but I can't. So I'm going to send Vanessa another email about that, to get those in. But but we still have like about an hour to one, so we can use this as our asynchronous time. And if we want to, we could write some smooth acceleration code in this time, or I could use this time to also work with Sandra, because she missed all of yesterday, which
I think
was
that would help her out.
yeah, because we went through like 5 hours worth of programming learning there yesterday. Um, so I'm sure there's a lot there that she would probably be interested in knowing. Um, but yeah, what do you guys think we should do?
I'm cool with kind of like logging off and doing like my unit 7s, kind of like having those ready to go and having those ready to like share or ask questions with on Monday. I don't know what Josh feels or Lisa feels.
Yes, I'm needing help. So
Okay. Okay. So I'll work with Sandra then, and then I guess the rest. How are you, Lisa? I don't hear too much from you every now and then, but are you doing all right? Or
I think I'm okay.
okay. Well, in that case, I'll be working with Sandra. Also, speaking of Monday, there's a very high possibility we might have a couple of teachers join us on Monday because and you might maybe you could use that time to kind of explain what we've been doing. I think there's a like Ashley Fontenot. She was out like the first week, so and she said and they're supposed to be watching the videos posted and kind of keeping up on their own. Um, but you guys, if you could explain to them what's going on. So it'll be Ashley Fontenot from Haynes Academy, and then also Raven Winchester. They her they've got her signed up to do like all the classes, and so since the engineering and this class was offered at the same time, so she spent like the first week with the engineering class, and she'll join us next week.
That happened to me too.
That's pretty bad, right?
Yeah,
Not
but
fun.
luckily I've been doing a lot of like the asynchronous work just outside, but I've done a lot of the projects like in science camps. So I had a lot of experience with a lot of the stuff already. So it was just kind of like orienting that to the engineering design process, but that wasn't too bad. So
Yeah. But that being said, like so Ashley and Raven will probably be joining us Monday. So if you guys would like, give them a warm welcome and kind of share what you guys have been up to the past week. Yep. Okay. So speaking of warm welcomes and stuff, so Sandra,
Well, you
where?
guys have a good weekend. I'm probably gonna log off because
Yeah,
I'm gonna be heading back to my house for the first time in a while.
yeah, that's fine. Yeah, you guys can feel free to log off. But and if you need any help, I'll be on here for a while. So if you need to pop back on, yep. Okay. Mhm. So where do we want to start, Sandra?
Well, I missed all of yesterday, so I'm not sure. Yeah.
Okay.
What did y'all do? Y'all just did programming yesterday?
So I'll pull up the Google site. I'll pull up the agenda here. So yesterday, so we did units 4 and 5 yesterday. So unit 4, so just like how we had that sensor that was like a poster project.
Yeah.
Unit 4, what's that?
I was agreeing. Yeah.
Oh, okay. So unit 4 is also another poster project, but what they're doing is they're researching different types of lifts and different types of accumulators. So an accumulator is kind of like a manipulator, but it picks up like a bunch of things and usually it picks them up and stores them, so it accumulates them. And that would be things like a magazine, like a magazine and a gun. That would be an accumulator, or a conveyor belt system would be accumulator, or even like a hopper, like some hopper that stores stuff that you would dump into. Those would be accumulators. And then are different ways of mechanisms for lifting things. And we went over those as well. So like you have your standard like elevator kind of lift, and you can kind of do that. There's a lot of ways you can do an elevator lift. You can use the rack and pinion gears to go up and down, or there is this really neat way where you can kind of use chain, and by tightening the chain, it actually kind of pulls up the lift. Um, and then also different types of linkages, like a 4-bar linkage is kind of what you have on your robot right now currently. And a
Okay.
4-bar linkage is basically, so if you look on your robot, you see how you have your kind of post that the arm's mounted to,
Mhm.
and then you have those 2 bars coming off of it, and then the claw itself would make up the 4th bar in that 4-bar. But you notice that it makes a parallelogram, right? So like no matter how it's turned, those vertical sections stay vertical. And that's no matter if it's down or if it's out all the way or if it's up all the way. It's always making that parallelogram, right?
Right.
Um, and so what's nice about a 4-bar lift as opposed to like a simple arc lift, with a simple arc lift, it's just 1 bar coming out and you just have like your claw or output mounted to it. And if you're moving with that arc, the the uh the output, like your claw, is in the same direction as your arm. And so as your arm's changing angles, your arm's changing angles. I mean your claw's changing angles too. But with your 4-bar lift, like what you have on your robot, no matter which angle the arm is at, the claw is always facing forwards. So it never changes its angle, which is kind of nice a lot of times. Uh, and so, in addition to like a 4-bar, you can also have like a 6-bar and an 8-bar, but that's basically just adding multiple stages of 4 bars. Uh, and so those kind of add up. Um, And then there's even like a very fancy lift. It's called like a double reverse 4-bar. where you have a 4 bar and then another 4 bar, and they're facing opposite directions. But you'll see a lot of competition teams when they need to raise up very high, they'll use a double reverse 4 bar. Because one nice thing about it, as opposed to a regular 4 bar or a 6 bar or 8 bar, is with those linkages, as it's raising up, it will swing out first and then pull back in again. So it starts in close, it kind of goes out a bit, and then it pulls back in. Um, but on the other hand, a double reverse 4 bar, when you build it, the output in actually goes straight up and down, straight vertically. So that's really useful because it doesn't swing out. And swinging out can be a problem, especially if you're grabbing something heavy. Because if it's swinging out, then that might send your center of gravity forward too much, and it might actually cause your robot to tip over. So you don't really have that problem with a double reverse 4 bar. And then another type of lift is like a scissor lift, and that literally works like a pair of scissors. So like when the scissors are open, it's really wide, but it's not raised up very high. And then as you close the scissors, then then that part gets narrower, but it's raised up more. And what you can do with a scissor lift is you can have multiple stages, like multiple scissors all linked together. And it's kind of like those old remember those toys with like the boxing gloves where you could like make them shoot out and retract in.
Oh, right. I know what you're talking about.
Yep.
I don't know what to call them, but
Yeah, so when you pull it open, it folds in, and then when you push
right,
it together, it shoots out. Yep.
right.
Yeah, so that's basically how a scissor lift works.
Okay.
Yep. So basically, just like with the sensor project where you assign each group a set of sensors, with the scissor lift, with the lift and accumulator, they're making a poster, and you basically assign each group one of those lifts, and they'll do a poster and present about it. Yep. So we didn't really spend very long talking about that. We went through that pretty quickly, because the bulk of our lesson was the Unit 5 lesson, and that was all our programming stuff. And so we actually went through each of those programming lessons, or each activity from Unit 5. So I guess we can pull up.
I do see that day 4, the video is up now.
Okay.
Yes. Which I mean, I guess I could go back and watch that, and try to go from there. And then if I have issues, ask class tomorrow. Monday, maybe.
Yeah. That would be one route to go.
I
If you
would
want
hate
to,
to have to go through the whole thing again.
yeah, yeah, it would be a bit much to go through the whole 5 hours again.
Right.
But we could, while we got this time, maybe we could look at one of the activities, and
Okay.
and we'll just pick one of the activities, and we'll go through it together, and maybe we'll have you share your screen, and we'll just walk you through writing the code for it.
All right.
Let's see, which activity do we want to pick?
Let's start with the easiest one. Well, I guess, or it don't matter. We could do the harder one, I guess, if we.
Yeah, I mean, yeah, if we did a harder one while I'm here,
Right.
versus you tackling a harder one on your own. Well, we could. What hopefully you will find is even with the harder activities, they're not really super hard. But
A lot of activities for Unit 5.
yes, yeah, there are. But instead of like being like a longer project that takes like a week, instead it's kind of broken into these little small activities. Most of these activities should only take like a class period to do.
Okay.
Maybe 2 at the most on some of them. Let's actually just start with the first activity though. So we'll look at the first activity, activity 0, because basically, if you can do this activity, you can do the other ones because it's basically just a lot of the same.
Okay.
So let's look at what this says. It says, in this activity, you'll write a code that will make your robot move forward for X seconds at full power, stop for Y seconds, and then move in reverse for Z seconds at half power. Create and use variables X, Y, and Z to set your times, but you must name your variables something meaningful. So don't use just X, Y, and Z as your variables, but like call them something else.
Okay.
Your left motor should be in port 1, your right motor should be in port 10. And then it asks you to go ahead and write the pseudocode, but we're just going to hop into writing the program. And then this is the solution for it. Okay, yeah. And then depending on your group, so this is where you would kind of assign, different people in your group.
Mm-hmm.
So like the first member of the group could do a forward time of 2 and a pause time of 4 and a backwards time of 3. And the second member of the group can do 3, 2, and 4. I think this is the solution. I think at some point I added in, because a lot of schools have 4-member groups because they just don't have enough equipment to share with 3-member groups. So I did add in a member 4 in there, and it had some numbers in it too. I think it's on the not the solution, but the actual activity. I think I added 4. So if you happen to have 4 members, so basically, so if you're saving that program in slot 1, they do the first one. If they're saving in slot 2, they do the second one, and so forth. So what we're going to do is you're going to write a code to do this. So we're going to have you share your screen. I'll stop sharing so you can share.
Okay. Now let me find my. So much going on here. Here it is. Okay. So we're going to start new, right? So new text
Yep.
project.
Yep.
C++.
Yep.
Okay.
And this is Unit 5, Activity 0.
I'm gonna put yesterday's date since it was.
Okay.
Not May 6th. And what do we? What's the description?
How about you say go forward X, wait Y, go backward Z, or something like that?
Okay.
Okay. So before we type any code, what do we generally want to do first?
Set the motors.
Yep, that's right. So let's set our motors. And for your robot, I don't think you have any gears on your robot, so I think you're just going to leave the left motor normal,
Okay.
and instead you're going to reverse the right motor.
Okay. Okay.
Okay. So what now? So at this point, we probably want to go ahead and make our comments for what we're trying to accomplish. And so uh, we're gonna need some variables. So want a comment or a section for declaring our variables, and typically we do that above our int main. Is where we're going to put our variables. So maybe put
No,
some
like one.
maybe put some space there, and then just make a comment that says declare variables. But to make a comment, you have to do the double slash first.
Okay. I'm gonna write that down. Make a comment. All right, and then I'm saying declare. What did you
Variable.
a variable?
Yep. And then let's maybe put another white. Yeah. Okay. And so that's where we're going to declare our variables. But before we actually start writing code, let's go ahead and plan out everything we're going to do with comments.
Okay.
So so inside our int main, like maybe under where it says begin project code. So the first thing we want to do is drive forward at 100%, right? For
Okay.
and we'll type that as a comment. So
Okay.
yep.
What do you mean by that?
So double slash.
Oh, right. Okay. So drive forward.
And I guess we could say at 100%, because what is it 100% for the? Hold on, let me look back at the assignment again. Yes,
Okay.
we want to go full power, so 100%.
You do a percent sign or type it out?
I do percent sign.
Okay.
Oh, you can do whatever you want. It's just a comment, so you can
Okay.
say
Oh, it doesn't matter. Okay.
yeah. So you can say it however you want. But we're going to drive 100% for X seconds, or in your case, X is 2. So you could say drive forward 100% for 2 seconds.
That look good. Okay. I think you're froze, or I'm froze. Okay. Where'd I go?
Sorry, I clicked the wrong button on one of my tabs and close it up.
Okay.
But yeah, that looks
Find
good.
my face either, so I wasn't sure. I didn't realize my video was off.
Yep.
Okay.
But yeah, that looks good. So we're going to drive forward at 100% for 2 seconds.
Okay.
And then the next thing we're going to do is we want to wait for, in your case, 4 seconds.
So do I put another line?
Yeah. So we'll have another comment.
Okay. And then we're going to wait.
Mm-hmm. For in your case, 4 seconds. Yeah.
Okay.
And then finally we're going to drive backwards at 50% for 3 seconds. So once again, these are all comments, so they don't have any bearing on the code whatsoever.
Okay.
But it's helpful sometimes to maybe plan out what you're trying to do in comments, um, so you kind of have an idea. Um, uh, and then some people will write their code first and then come back and comment it later to explain it.
Okay.
Um, but you can also use comments as a planning tool, like what we're doing right now. Um, and so I would actually probably put some white space between all that, just like
You talking about or
like in between each of those lines,
okay.
add some white space because
In
each of
between
those
the
is going to
comments
be
like
yeah.
that?
Hmm.
Well,
Yeah, that's fine.
okay.
Okay, so and that's what we want our program to do. That's what the the activity says to do. So we're going to go forward at 100% for 2 seconds, wait for 4 seconds, and then drive backwards for 3 seconds.
Okay.
Um, now, so let's now actually do our variables now. So we're going to declare variables. We're going to go where we said declare variables.
All right. Huh.
Yeah. And so we're going to need 3 variables here. Um, now, every variable is going to have 3 parts to it when you declare it. The
Okay.
first part is what type of variable it is, like what type of number or data you're trying to store. In this case, all our numbers are whole numbers, so they're going to be integers. So so we'll start off by saying int. That means we're going to store an integer,
Okay.
and then we'll have a space, and then we will come up with a name for a variable. So there are some rules you have to follow when naming variables. First off, they can't start with a number. Um, they can't have any spaces in them. They can't have any special characters in them other than underscore,
Okay.
and they can't be something that's already being used. Like for instance, you can't make a variable called time because
Okay.
time is already being used by the program for something else. Um, so in this case, we want a variable for when we're going forward. So what would be a good name for that variable?
Mm.
I mean, you can call it whatever you want, but some suggestion. But you want to be descriptive for what it's trying to do, because I've had some students just call them like Jerry and Phil and stuff like that. But that's not super great because you don't really know what you're using them for. But how about call it forward time, since it's the time for going
Oh,
forward?
okay.
Does that sound good?
That sounds good.
Yep. And typically, a good habit to get into is when we have like a 2 word thing, we use camel case notation. So we'll capitalize the T. Yep.
I was just about to ask that.
Yep. And that's not a hard and fast rule, but it does make it easier to read. Yep.
Okay.
Okay. So now we'll have another space.
Oh,
Uh,
sorry.
yep. And now we're going to do an equal sign. And now we're going to, and another space. And now we're going to assign a value to that forward time. And I think it was 2. Yep. We were going to go for 2 seconds. And then to end the line, we're going to do a semicolon. Yep. So that equal sign is what's known as an assignment operator. And what
Okay.
that's doing is assigning the number 2 to forward time.
Okay.
Okay. So now that we created forward time, we're going to create another one. So
Is this the one to wait for 4 seconds?
yep.
So would it be int
Hmm.
wait time maybe?
Yeah, wait time sounds good.
And then equals 4.
Mm-hmm.
Okay.
All right.
And now we're going to do
Yeah, that's right. And I would probably just do it some more white space,
okay.
or yep, just to separate that out. But yeah, so those we've declared our variables, so we're going to use those later in the code. So we'll call on those later. So now that we've done that, now it's time to actually write the rest of our code. So we'll start with the drive forward at 100% for 2 seconds. So let's start with that. So under where you have that is where we'll, so like probably on line like 95.
Yeah. Okay. All right.
So this is where we're going to write our code to go forward at 100% for 2 seconds.
Okay.
So, what do you think is the first thing we want to do?
Hmm. So would we have to start with the motor?
Yeah, what do we want to do with our motor first?
Hmm. So we want it to go forward.
Mm-hmm.
I don't know.
Okay.
Would you-
So there are 2 ways we can do this. But the first thing we probably want to do is set the speed of our motor, set the velocity of our motor. Now, there are 2 ways you can do this. There is a command called set velocity that we can use,
Oh, okay.
or the spin command. Even though it doesn't really say it there, you can actually in the spin command you can also set the velocity in that command. We didn't really introduce at this point. We haven't introduced that yet, so normally the kids would be doing the step velocity. Now, the way you could type that out, you could either drag that in if you wanted to, or you could type it out. Either way.
Okay.
So you see on the side where it says motor set velocity 50%.
Right here.
Yep. So you could just drag that over if you wanted to and drop
Okay.
it in. And we would simply just need to change that 50 to 100.
Oop.
Yep.
Okay.
Yep. And now we also need to do that for the right motor.
Just do the same thing, then change it.
Yep.
Okay.
So notice how it's always kind of defaulting to saying left motor.
Mhm.
And that's because the left motor is that first motor that you declared.
Fine.
And so it always kind of defaults to that. Okay. So now that we set our speeds, now what do you think we need to do?
So now we have to do the time for how many seconds?
Well, even though we set a speed, we haven't actually turned on our motors yet. We're just telling them when we do a set velocity, this is saying that, okay, when we run our motors, we're going to be running them at this speed.
Okay.
That's really all set velocity does, but it doesn't actually turn the motors on.
Okay. So which one turns the motors on? The spin?
Yes. So spin is going to turn on the motors.
So do I just go below this?
Yep.
Oop. Okay. Stop. So would that be like left motor? Oh. Dot spin?
Mm-hmm.
And then
And yeah, then we have to open up a parentheses.
okay.
And inside here, we have to specify what direction we want it to spin. So we can either say forward or reverse.
Will we go forward on the left?
Mhm. Yep, because we're driving forward.
Right. Okay. And then close
Yeah.
or
Yeah. Close parentheses and then end it with a semicolon.
okay. And then right motor. Spin. Is this the one we went the reverse on?
Well, that
Or
doesn't
or
matter.
forward?
You want them both to be in the forward direction now, so you want to just say forward.
Okay.
Yep.
All right. Okay.
Okay. So we've set the speeds, we've turned on the motors. Now what do we want to do?
Okay. So now we got to do the time.
Yep.
Okay. So it's got to be turn time.
Or forward
Right?
time is
I'm sorry, say it one more time.
you mean forward time?
Forward time? Is that what
That was the variable you had.
okay. All right. So we do
So you're going to say wait.
right. That's what I was thinking. So we do wait and then forward. Is that right?
Hmm.
Okay.
And then you have to do a comma,
And
and you
then
have
say
to say what units that's in, which is in seconds in this case.
okay.
Okay, and then semicolon.
All right.
Okay, so now we spun the motors. We've waited for 2 seconds because forward time is 2. And now what do we want to do with the motors?
Let's see. So we did the forward time, the wait time. Tell it when to stop. No, we got to do backwards.
Well, no, we need to stop the motors, right?
Right. Okay.
Yep.
So, we would do left motor stop and right motor.
Yes.
Both. Okay. It would be dot stop.
Mm-hmm.
Okay.
And
And
we still need to do the open and close parentheses,
okay. And
but we don't have to put anything inside. And then semicolon.
okay.
Yep. Okay, so we've set the velocities for the motors. We started the motors. We're waited for 2 seconds, and then we're stopping the motors. So that should be what's necessary to go forward for 2 seconds.
Okay.
Let's go ahead and hit build to
Mhm.
see if we have any errors there. Okay, so it doesn't look like we have any errors, so that's great.
Okay.
Okay, so we're done with the drive forward part.
Mhm.
So now we have our wait part. So we're going to wait for 4 seconds.
All right. Do we just put in wait?
Mm-hmm.
Okay. And wait time.
Yep.
Comma. Whoops. And then seconds.
Yep.
Okay. Do we do the parentheses?
Well, yeah, I think it did it automatically, but yeah, you do have you do a parentheses, a closed parentheses. Yeah.
Okay. And then semicolon.
Yep.
Okay.
Okay. I would do, and that's it for the wait, right?
Right.
Okay.
Okay.
Now, for the drive backwards, since we typed out all that code for drive forwards, how about we copy all
Okay.
that? So let's copy from lines 95 to 101.
Okay.
Because we can just change that up a little bit to make it drive backwards, right?
Okay.
So, and if you want to, you can adjust that to make it line up.
Okay.
So we wanted to go at 50% this time.
Okay.
And then instead of forward, we want to go backwards. or and it's reverse is what you say. You don't say backwards. So
Okay, so you say reverse.
and then instead of waiting forward time, we're going to wait your backward time. I think is what you called it. Yeah.
Mm-hmm.
And let's build that and see if it builds. Yep. So it doesn't look like you have any errors there either.
Okay.
And so if we load that on our robot, that should work. So it should go forward at full speed
Okay.
for 2 seconds, and then it should wait for 4 seconds, and then it should go backwards for.
I realized that I left my cord for that at the classroom, but tell me again how you load that on there. I know where to plug it in.
Okay. So
Automatically go, but we did something else.
okay. So what you would do?
Brain?
Yeah, you click on the brain button and you hit connect,
Okay, yeah. I
and
remember.
if it's plugged in, you'll see it.
Right. I remember that now.
And then it should turn green once it's connected, and then that build button should change into a download button.
Okay.
Now, I seem now that I'm thinking about it, we did do a couple of extra things. You could get it from the video. I guess we could go over it now. One thing we did do is we also made it display what it was doing on the screen. So, like for instance, like on the screen, we made it say, like on the brain itself, we made it say that it was going forward for 2 seconds and stopping for 4 seconds and going backwards for.
So how do you?
So
You have
I
to
guess
type in the code for it to do that.
yeah. So there is some code that we can write to do that.
Okay.
So so yeah, let's go over how to do that too. So okay, so let's add a line before line 95, like between there, because so right at the front of that, yeah, we'll
I want to erase. That's not going to
I
erase.
don't want to erase. Just press enter to, yeah,
Okay.
yeah. So we're going to add some code there for writing a line. So you can find this under looks on the side. Do you see how you have like motion and looks and everything like that?
Okay.
And the command we're going to use is brain screen print. So you can literally just drag that in. And then to change what it says, so whatever you put in the quotation marks is what it's going to say on the brain.
Okay.
So right now it's saying vex code, but right now we could say drive forward. And you can put spaces here, by the way, because you could just write it out like a normal sentence or whatever if you wanted to. But
okay. Oh, I thought it would replace the vex. Get rid of that. Okay.
And maybe we want to say like how long it's driving forward. So we have that variable stored, right? So what we're gonna do is we're gonna grab that variable, and whatever it's in that variable, we're gonna put there. So to do that, so to do that, what we're gonna do is instead of saying like the number 2 and like hard coding that in, instead we're gonna do %d. %d. So that's what that's gonna do is %d. Where we're getting this from is, do you see on the side with looks and it says brainstem print and vex code, and you see that question mark there? If you click that question mark, it'll actually bring up a help on how to use these different commands.
Oh, okay.
And then one thing it has in there is that printing values. and it gives an example of that. So what we're doing is, since that number we have is an integer, that's why we're using %d, because that's
Oh.
for a signed integer.
Okay.
Okay, and so let's go back. Well, you can close that for now, though. So back to our brain screen print. After the quotation mark,
Mhm.
we're going to put a comma. Well, actually, hold on. Before the quotation mark, we're not quite done there. Before the quotation, let's put a space and say seconds. So the %d is going to be whatever number that we tell it. And so it should say drive forward for 2 seconds if we did it right.
Okay.
Okay, so now we need to tell it what %d is supposed to be. And that's where we're going to, outside of it, we're going to put a comma outside of the quotation, but still inside the parentheses. And then we're going to say what that variable is. So in this case, it would be forward time. Okay. And what this should do is it should drive forward for 4 time seconds. And forward time in this case is 2. So on the brain, it should show drive forward for 2 seconds when this runs.
Okay.
Now, what would be really nice is if after it showed that, we skip to the next line on the brain. And then when it's waiting, we tell it to wait, for however long seconds. So the next thing we're going to do is right under that line, we're going to grab that brain screen new line. And and just plop that.
Thought I was dragging it.
And what that does is it just moves the cursor to the next line on the brain.
Okay.
So it just moves it down to the next line on the screen. Okay, so since we're basically doing the same thing for the other stuff, let's just copy those 2 lines of code.
You talking about these two?
Yep.
All right.
And then let's do the same thing for our wait. So like before line 109. And we'll just paste those in. And then we'll just make some changes to that. So instead of saying drive forward, we could say like maybe we're waiting for wait time seconds. Or you should say, I would just say wait for blank
Okay.
second. Yep.
And then it was wait time.
Yep.
Okay.
Okay. And then
Okay.
we can do the same thing for the backward part.
Oh, no, that didn't work. Okay, let's try this.
Yeah. And then we could just say drive backwards for and this time it would be the backwards time seconds. Yeah. And let's hit build and make sure everything compiles okay. Oh, we got an error. So it says problem with backwards time. So go up and oh, it was just backward time. Yep. Okay.
Okay, that's what it was.
All right, let's try compiling again. And okay, no problems.
This automatically saves, periodically as you put stuff
Yeah.
in.
So do you see next to it where it says saved? As long
Mhm.
as it's saying saved, and that means it's being saved. Yep.
So I could actually access this through my files, like here on my Chromebook.
Yeah. Well, it depends on the file location, but I'm pretty sure that's the case. So Um, yep, that's it right there.
All right.
Okay, so that was that first program.
Not too bad.
Yep.
Okay.
And honestly, most of these other programs are going to just be a variation of that. So it's going to be like you're going to be setting the speeds, you're going to be starting up the motors, waiting, and then stopping the motors.
I
And
think that's something I really need to work on too, is finding out, all those calculations you were talking about, with the wait time and unless they give it to,
yeah, in this case, they
with
just
those
gave it.
conversions, I really need to work on that.
Okay, so before we go, then, one of the lessons is the basketball drill.
Uh-huh.
And for that basketball drill, you're supposed to go forward 2 feet and then go backwards 2 feet and then go forwards 4 feet and go backwards 4 feet and so forth and so on. Well, yeah, so it's 2 feet, 4 feet, 6 feet, and then 8 feet.
That's in that, but all that information's in the activity, right?
Yeah, but you need to but you need to actually calculate that
Okay.
at least for the 2 feet because the 4 feet is just double the 2 feet
Right.
and so forth. So so do you think you can do that calculation for your robot?
I don't know.
So
No, let me pull it up. This was which activity? Oh, let's see, 7.
it's going to be I think it's going to be activity 4. Yeah. Yeah, I think it's 5.1 program basics and it's going to be yeah, basketball drill.
Okay.
Um
So, and I mean, y'all talk about it like it's like, I don't know. Physics,
second nature, yeah.
like,
Okay.
I, I don't
So
know. I never was really good at science and physics and all that. I mean, I was good at working equations, but it's
okay. So
a little overwhelming.
so let's just kind of go through the process. So we know we're trying to go 2 feet
Okay.
and we need to figure out how much time it's going to take to go 2 feet, right?
Right.
So basically what we're trying to do is take that 2 feet and turn it into seconds.
Okay.
So so let's
Right.
like make our
Trying to
picket.
go from feet to seconds.
Yep. So we're going from feet to seconds. So
All right.
let's like make a little picket fence, and in the first spot we'll put in 2 feet.
So we start out with the 2 feet.
Yep.
Right. So the bottom line, you got to have to feet.
Yeah. So we'll carry down the feet,
Okay.
and what can we turn the feet into?
Inches.
Yep. So we'll put inches on top.
So we're going to put 12 inches on top and 1 foot
Yes,
on the
that's right.
bottom. Okay.
Yep. So we'll have 12 inches on top and 1 foot on bottom.
Okay. And
Okay.
then,
Now we'll carry the inches down.
mhm.
And what can we turn inches into?
Are we doing rotations?
Yes, we could turn it into rotations.
Okay. So top would be 1 rotation.
That's right.
Okay.
And then
And
how far do you travel in one rotation?
2 feet. I mean, no, well,
So every one rotation of the wheel, how far will the wheel travel?
um, would be 24 inches.
It wouldn't be 24 inches.
Okay. I'm confused. Okay. So,
So okay, so I have my wheel, right?
okay.
Like my 4-inch wheel. And I guess you
Oh,
don't yeah.
4 times pi.
That's right.
Okay.
We're gonna do the circumference. So 4 pi.
Circumference of the wheel. Okay.
So every one rotation of the wheel, we're going to travel the circumference of the wheel. So we'll have 1 by the rotation and 4 pi by the inches.
Okay. All right. Gotcha. And that gets rid of the inches. All
Mhm.
right. Which means
So now we'll carry down the rotations.
Mhm.
And what can we turn rotations into?
Seconds.
We'll turn
I
into
picked up a
something
few
else
more
first.
things. Okay.
So when you think about RPM, what does the M stand for in RPM?
Minute. So put them
Yep.
in minutes. Okay. So
Yes.
on top.
Yep. So we'll put minutes on top.
Would it be in 1 minute?
Yeah. So 1 minute will travel so many rotations, right?
Right.
And
Got
so if it's 100 RPM, which would be the case if we're going at 50%, 100 RPM would be 100 rotations for every 1 minute.
Okay.
So we would have 100 by the rotation and 1 by the minute.
Okay.
Okay. And then
Okay.
finally, we can carry that
Still see
minutes
my
down.
screen? Can you still see my screen?
I can still see your screen. I can't really. You might want to turn off your sharing though, so I can see your.
Okay. Let's see.
Okay.
Is that looking good?
Yep. And then we need to just go one more step.
Okay.
So we'll carry the minutes down,
All right.
and we can turn that minutes into seconds now. So we'll put seconds on top.
It'd have to be 60 seconds. Will it be 1 minute
Yeah.
on the bottom?
Yes. So
And then
there's
60 seconds on top.
Yep. So
Okay.
because there's 60 seconds in 1 minute.
Okay, let me do this now. Let's see. Oh, oh. Two, oh, oh.
So
I
what
did
did-
I did times. Hold on, let me let me divide. I was like, that is a million. Okay, so 1.15.
Yep, that's also what I got.
Okay. All right.
So now that you have that value, now you know if you want to go forward 2 feet, you want to turn on the motors, wait 1.15 seconds, and then turn off the motors, and then stop the motors. Yep.
Okay. So say that one more time. So we're going.
So so if you're traveling forward 2 feet, what you'll do is you'll spin the motors, then you'll wait for that many seconds, 1.15 seconds, and then you'll stop the motors.
All right, so we're spinning them. We're waiting 1.15 seconds. And then we're gonna stop.
Mm-hmm.
Okay.
And they'll have you going forward.
All right.
Okay.
So we're going forward 2 feet. Okay, spin motors. What did you say after spin motors?
Then we're gonna after you spin the motors, you're gonna wait.
Okay, yeah. Okay. So that's 1, 2. And then we're gonna wait 1.5 seconds and then we're gonna stop. Okay.
Yep.
All right.
And that will be the going forward part. And then the going backwards would be the same thing, but we're gonna spin the motors in reverse. Wait that same amount of time, and then stop the motors again.
I got you. So then we So would we reverse 2 feet
Yes,
and
because
then 2 motors and then reverse or wait 1.5 seconds and then stop?
yeah, it's actually 1.15, not
I mean,
1.
yeah, I got that written down. I don't know what I. All right. All righty.
Yep. And then you would repeat the process for the 4 feet, but the 4 feet it would just be twice as long.
Right. You just double it.
Mm-hmm. And then the 6 feet would be 3 times as long, and the 8 feet would be 4 times as long.
Right. I got that part.
So basically, when you're writing that code, you're just going to write your forward, and then you probably can copy all that and then do your backwards by just changing forward to reverse. And then once you have that 2 feet, you just copy all that, and then you paste it, and you change it for 4 feet, and then paste it again and change it for 6 feet, and paste it again and change for 8 feet.
Okay.
So, uh, so it's overall, it's not really super difficult
Okay.
as long as you can kind of break down the problem into sections.
Right. It doesn't seem as difficult. It's just getting those numbers right.
Yeah.
I think is going to be my biggest issue is doing those conversions. I'm gonna practice on some of those this weekend. Of course, I do have Miss Rhonda there. If she can get unbusy this week, maybe she could help me a little bit. But I think I will have. I don't know if I'll make it through this training, but anyway,
You're doing fine. You're doing fine.
I mean, I'm excited about it because I like to learn new things, but it's a lot to take in, I guess, in this few days. But I'm always nervous I'm going to mess up my students, you know. But I gotta have
They
my
won't even notice.
yeah. All right. Well, I'm gonna try to write this code. I may send it to you and see what you think. Well, I guess I can do build and that when I build it, it'll check it and see if it's right.
Yeah. And well, it will check for any syntax errors, but if you have like any semantic errors, it won't check. But when you load it on your robot and test it, then you'll know for sure if it's working or not. Yep.
I gotta go back up to the school and get
So a micro USB, yeah.
yes.
Unless you have a junk drawer that has one of those cords in it.
I don't think I do. I might. Is that the same as the cell phone charger that's
Yeah, like the older
the
cell
older
phone
ones?
charger.
Yeah.
Yeah,
Oh, okay. I may have one of those. I'm gonna look around and see. And
yeah.
then okay. Well, thank you so much.
Sure. I'll see you guys Monday.
Sounds good. Have a
All
good
right.
weekend.
You too.
All right.
Bye.
Bye.
Bye. I was
Oh,
gonna
bye,
see.
Josh.
I didn't realize it was gonna be that late. I was gonna see if you finished earlier, we could do the acceleration thing. But we can do it.
Oh, that's what that we were. I mean,
Yeah. I mean, if you want to, I can show you what I got for my code so far for the
oh,
other
you've been working on it,
the
or are you working
last
on something
couple.
else? Yeah, sure.
So gotta move everything around. All right. So this is for wait. I'm sorry. This is for activity 3.
Okay. So this is
So
based off of
I just
time.
did the one variable. Um, since it's just going back and forth, I didn't really see the point in doing a whole bunch of different variables. And I
Yeah.
just did 2 feet.
Mm-hmm.
Uh, and then I went in and I set my velocity initially, like normal.
Mm-hmm.
And then I just did it as chunks of 2 feet, 4 feet, 6 feet, 8 feet, forward and back.
Yeah, and that looks good.
And
Like you just multiply by
I did the
2
multiplier by
for
the
4.
negative.
Mm-hmm.
And then whenever we went 4 feet, I doubled it. And then, like you said, 6 feet, I tripled it. And 8 feet, I quadrupled it. And
Yeah,
I
and,
feel like
and
that should be pretty accurate at least.
that should work pretty well. Yeah.
Okay. And then I think I'm done with this one now. I'm really close if I'm not. So this is the century one.
Mm-hmm.
So for the variables here, turn rotation, and I try to put down that I have gear ratios, so that's why my numbers might be weird compared to some other people's.
Okay.
Um, So I commented that just to make sure people could see it.
And are those times in milliseconds, I'm assuming? Or are they
No,
in
these are degrees of rotation.
degrees? Yeah, I'm sorry.
I'm
Yeah.
doing the encoder one. So
Okay.
these are degrees of rotation, which I think this should be correct.
Okay.
Or fairly close at least. I'll have to check it obviously. But and then so that's the first section, second section, third set. Oh, we need to add one more for it to finish. And then I don't need a so wait a second. So 3 degrees, so that's straight, turn right. So that's right, turn right. So it's down, turn right. So now I need just to the left. So I just need this last part to get me back to the beginning.
Yeah, and you don't need that last turn. Yeah, unless you just wanted to be facing the same direction.
The original direction, yeah. Okay, so that should be. I think it's okay. It builds fine, so
Mhm.
that part looks good. And then the question is my math, but I can check that. That's not a hard check. Should be close, I think.
Yeah. Yeah, that looks good.
All right. Well, yeah. I mean, I figure it's already after 1, so I figured we can do that some other time.
Yeah.
But you got me curious because that uh, I figure it's just like a math. It's a basic math equation that you have to do to figure it out. But yeah. Well, all right. Well, thank you, sir. Have a great weekend.
You
And I'll
too.
see you in the later part.
Okay. All right.